Right, so today I'm just going to, obviously one can't cover the whole topic of every geophysical technique for diamonds in detail. So what I've done is I've given a couple of these talks before, and I've thrown out all of the introductory stuff, assuming that everybody knows something about geophysics already, and I'm just going to sort of whiz through anything like that, and then get into the juicier stuff of some real case studies and also new developments, which I think everyone is interested to see because of the whole drone thing, radar, AMT techniques that we're not that used to. We're all used to these techniques here, magnetics, which is by far the most common and important for anyone doing any kind of exploration. But then we've also been, with magnetics goes the radiometric stuff, gamma ray spectrometry, and then we've also often used gravity in the past and some EM. But the newer stuff, the AMT, drone, UAV platform, plus radar, and to some extent geophysical logging. It's been around a long time, geophysical logging, but I'll just run through that stuff again because occasionally we've done something innovative there. So if I just quickly remind you about the Earth's magnetic field, the only critical thing to remember really is that the field comes out vertically at the poles and it's horizontal at the equator. And a lot of people lose track of that, and they go, well, why is it not a dipole? Why is it different? Why is it a high, etc., etc. You have to know your latitude. The big thing with magnetic field is, depending on your latitude, the magnetic body, a magnetic anomaly of any body looks totally different at the equator because it's horizontal, and at the poles because the field is coming out vertically. So just to brush up on magnetic susceptibility, this is the ability of any material to enhance applied magnetic field. So in our case, we have a magnetite grain, and within magnetite grains in any rock, there are domains. They're either small or they're large. And what happens is we apply the Earth's external field, this applied field, and that magnetic domain either enhances it or subtracts from it or does something to it. So we get an addition of the field or a subtraction of the field, depending on whether these domains are superparamagnetic or magnetic, etc. Just remember that not all minerals do have a magnetic susceptibility. The most susceptible minerals are generally oxides, although some sulfides are as well. And I'll draw your attention to magnetite over here. We're talking SI units here. Magnetite is by far and away, with titanium maghemite, the mineral most responsible for any kind of response to the Earth's magnetic field, any kind of magnetic response. But if you look at this guy here, this is what's critical when it comes to kimberlites. And you'll see that it can actually go right up into the magnetite field and the maghemite field, into the millions, 3.8 million. So a lot of people overlook the fact that ilmenite can be, in fact, very susceptible, and it can also not be susceptible. It can be very low. So that's the problem with kimberlites. Some of them are highly visible in magnetic fields or in a magnetic survey, and some of them are not. And that all depends on the iron content and many, many other factors. But ilmenite is the mineral that we're looking at, really, not magnetite. I'm just going to run into some filters quickly and show you the effects, because a lot of people know what mag is and what a kimberlite looks like in a magnetic survey, but don't fully understand what it is when we do with these filters. So I'll just remind you, normal polarization in southern Africa at this latitude, which is around 30 degrees south, sort of in the subtropics, we have a normal dipole, where the high is to the north and the magnetic low is to the south. However, often we have some remnants thrown in there, and the remnants is caused by usually some magnetite in the rock, and it has a memory of where it was when this rock was injected, and that can become quite useful. So if we reduce this to the pole, i.e. we're no longer hot at this latitude, but we're at one of the poles, we should just see a big round red blob. But actually in this particular case of a kimberlite pipe, I reduced to the pole and the low is still showing strongly. That's a very quick test for remnants. If the low is still showing strongly after you've done reduction to the pole, then you can immediately say that you do have remnants. So that's one little trick. Let's look at other effects of filters. If we look at these three bodies here, these are not necessarily kimberlites, but they are three dipoles. And it's quite good to show these because you see here we have a perfect normal dipole. And then you have these other weird little guys that generally would say, oh, they're dolerite or something else. And then something that looks like it's attached to a big sill, but the low is giving it away. I'm just going to show you the effect of running spatial filters on these. This is the total field. So what we do, if we reduce to the pole, we put the high directly over the body, and if there's no remnants, there's no low left. So you can see that it's just tiny little lows here. You could basically write them off. So you could say that these bodies are not exactly remnantly polarized. They're fine. And what's happened is we've managed to move the high slightly south. I'll just show you the previous slide again. The high actually moves south towards the midpoint between the high and the low. And it puts the high directly over the body, which is why everybody loves it so much. The problem with this is that when you get to the equator, reduction to the pole does not work that well. We tend to blow up north-south features and becomes very unstable because we are rapidly approaching 0 degrees and we're doing trig with 0 degrees. So you've got to be aware that close to the equator, reduction to the pole is not the best thing you should do. It works best at high latitudes. Vertical derivatives basically sharpen up everything. So if I go back to this previous, you'll see that this magnetic texture in the background here, this ripple effect, is not as obvious as it is when I sharpen it up with the derivative. And also, you'll find that when you do TMI, total field, and reduction to the pole, these magnetic highs are much bigger than the body. What first vertical derivative tends to do is make them smaller and put them and create an anomaly that is more in keeping with the size of the body that's causing it. You'll see this is first vertical derivative of the TMI, so we still have the low, and you'll see how much sharper everything's become, how much smaller, and then also this ripple texture, which is the background geology, is showing up much more clearly. And even more so if I do a second vertical derivative, this really breaks the body up into its component parts. You can see that some of these were in fact lobate or two bodies, very, very narrow features popping out. And what's lovely about this second vertical derivative when you have good mag is you can now do geological mapping quite sharply. It pulls out these contacts very well, and I can say with confidence that to the right of this line, where magnetically it's quite smooth, and to the left of that line, that's a geological contact, because I have this very, very strong texture over what may be a dolerite or gabbro here, and then I have some sort of sediment there, and you can see a tongue of that coming in. So they sharpen things up. And when you look at analytical signal, which everybody has heard of, and we always do when we're looking for kimberlite pipes as well, what it does is it cuts through the clutter. Previously, everything was quite noisy and difficult to keep your eye on any one thing that might be a kimberlite. But when we do analytical signal, it tends to show the most magnetic features on the map. It puts a big red blob over them, which we all love. And also it puts it directly, the anomaly directly over the body, just like reduction to the pole. It just works on gradients. So an analytical signal in a busy terrain can often help your eye adjust to the noise. You can adjust the colors, get rid of all the background noise, and say, okay, I only want to see the most magnetic things in my magnetic map. And that's what it's done here. When I show you what it does in profile, so say now we are looking at a line of magnetic data in profile, and this is your kimberlite down here in yellow. When we reduce to the pole or do a magnetic signal, analytical signal, we have originally at this latitude in Southern Africa, we have a low and a high, and you'll see the body is positioned somewhere between the low and the high, usually a little bit south of the high. But what happens when we reduce to the pole or the analytical signal, it removes this dipole, gets rid of the low, and the black curve now shows you a nice high, only a high directly over the body. That applies to both reduction to the pole and analytical signal. In section, when we do a vertical derivative of the TMI, it just sharpens it up, moves the low closer and the high more in keeping with the size of the body. And it basically tightens up, so you can say between the high and the low, And in this case, on top where the high is, we've shifted the high a little bit south, is more or less where my body is. I've got a much more accurate idea of where this body is and what its size is, rather than having this spread out red curve. I've now got this much tighter black curve. And of course, we can also now do 3D modeling of kimberlitic bodies of dipoles. So if this is my magnetic dipole that was recorded in the ground magnetic survey on the top left here, there's something now that GSSA supplies called voxy modeling, which is named after the voxel, the volume element, as opposed to a pixel, which is a picture element. So what it does is it puts a volume beneath the survey in the Earth, and it has millions and millions of little cubes, and it gives each cube a magnetic susceptibility. And it says, okay, how do I have to vary the magnetic susceptibility of each and every cube in this volume of space beneath the survey until I've got a closed volumetric area that on its own, when I clip it down to the highest magnetic susceptibility values, that will explain that magnetic anomaly. And you can actually generate the field again from this body and compare them directly. So you have the measured field from the magnetometer, you have the generated field from the model, and you can see that the two would be identical. If not, you've got a slight error, but it's never going to be perfect. But at least you can say, wow, this body pretty much generates that dipolar anomaly over there. That's what my body looks like at depth. And I can measure, of course, how deep it is, how large it is, can even create measure its volume. Of course, this has problems. We don't know anything about the size or the depth of the body at the time we're usually working with it. So we have to decide what magnetic susceptibility level to clip in the voxel. And depending on what level you clip it at, you either have a bigger body that's shallower or you have a smaller body that's deeper. And that is always the conundrum with geophysics. So that's just to brush you up again on magnetic stuff, so we can move on to the drones themselves. Basically, a drone is just a kind of a nickname for an unmanned aerial vehicle, a UAV. Most people prefer that name, but throughout I'm just going to use the word drone because we use the slang. And essentially what you're doing now is you do have fixed wing drones, but in general for this kind of thing we use hexacopter drones. So they have 6 blades, and we sling a magnetometer up to 3 meters below them, because obviously it's an incredibly sensitive piece of equipment and you can't have the whirling blades or anything metallic in the drone itself affecting the magnetometer. There's been some great new breakthroughs in terms of magnetometers too. We used to have those things the size of a beer mug, cesium vapor magnetometers that we all grew up on. But now what we're using is what is called an MFAM, which is a microfabricated atomic magnetometer. And you're looking at it here where my mouse is. That's a 5 Rand coin. So this tiny little brick, not much bigger than a 5 Rand coin, is now what we call the magnetometer inside some of these birds. You don't have to have it in an aerodynamic bird. You could literally hang that thing on a string, but it's much better to know the orientation first of all, so that you keep the nose of this bird, this geometrics bird, along the line direction, because like most magnetometers, they're actually sensitive to the direction that the field is passing through them. And in addition, we have 2 of them in here. We can have one at one orientation and one at another orientation, and therefore when we flip the drone around, we can pick up the magnetic field more accurately with one of them, one on the other. We can take an average, or we can say, right, we've got a better result from this drone in that orientation. Or you can just have them both in the same orientation. We've got no issues with the field inclination, and you can either average them or use the one as a backup. And what we find is fantastic is that the one is a backup. So if ever anything goes wrong and one of these little guys is spiking, tends to serendipitously happen that the other one is working well on that day. It's very seldom that both of them give problems on the same day. And even better, you can, as I say, take the average of the 2 and get a really accurate result. So this bird that we use is called the Geometrics Mag Arrow. It has 2 MFAMs inside it, which you can orientate. And we sling it with its nose forward in front of the drone, below the drone, about 3 meters below the drone, on nylon string. And the remarkable thing about this bird, this magnetometer, is that it takes a reading we used to take a reading every second. What we considered a really good rate of sampling was 1 every second. And then when we started really good airborne platforms, we used to take 20 readings a second and consider that fantastic. So that's 20 hertz. This little guy samples 1,000 times per second. So every second we are getting 1,000 readings, and that's because of the new design of these MFAMs. They work on an optically pumped laser system, and they can take this many readings in a second. What's fantastic about that is, of course, you can pick up every tiny little blip along the flight path, but also you can do electromagnetics. You are basically sampling the B field of an electromagnetic response, i.e. the magnetic field extreme blip in the magnetic field when you energize something with an electromagnetic field. So what these new magnetometers are doing, and this is where things get exciting, is that they're allowing us to do electromagnetic surveys by sampling the B field with a magnetometer. All we have to do is lay the loop on the ground, energize whatever's in the ground. We don't know what's there. We fly what is, after all, just a mag survey. And if we're clever, we can sample the B field out of that in very, very early times. And this has only become available of late because we are now able to sample the magnetic field so rapidly. Okay, why would we do drone surveys? Well, they fit in somewhere between ground mag surveys and aircraft surveys. And the reason is that companies like Excalibur, NRG, all the airborne companies, they won't mobilize for a small survey. They basically say it's too small, we're not interested. And there are certain sizes of surveys that fit in there, right in between the ground survey size and the airborne survey, the aeroplane survey size, where drones fit in just nicely. So they fill a gap. Some ground surveys are in very, very difficult areas. They're just too large to do quickly. They're mountainous, they're full of thorns or forest or swamp, choose your pick, out at sea. You can't do ground surveys, but they're too small for an aircraft to take them on. So they fit in very neatly in this gap. They can work in very rough terrain, and we can do about 10 times as much as a ground survey. So it's quite a lot less than an aircraft would do. So Excalibur would do 700 Ks in a day. We can do at the moment about 100 kilometers in a day, but that's 10 times more than you can do on the ground. So as you can see, even with that, the drone survey is fitting in right in the middle. And they're good for terrain where it's too tough to do it easily on the ground. So say, for example, you're in Angola and you've got guys working alluvial gravels and it's dangerous. They don't want you messing around. They don't want you walking in amongst their mining operation. You can fly a drone over and hopefully they won't throw sticks and stones at it. And we're currently flying a drone survey in Swaziland where the kids have been throwing sticks and stones at the drone the whole time as it goes over. So you do need community liaison where you can get it. Okay, so that's why we do it. Why only magnetics? At the moment, it's not only magnetic. It's just that magnetics was the quickest, the easiest, and the lightest bird to manufacture. Electromagnetics, radiometrics, things like that are heavy. And when we're using hexacopter drones, we can only take so much payload, as they call it, anywhere from 1 kilogram to 5 kilograms if it's a big drone. So we just can't carry what an aircraft can carry, unless you use a bigger and bigger and bigger drone, and eventually you're basically using an aircraft. So somewhere there's a cutoff in the size. But MAG was, because it's such a popular thing, MAG was one of the first to go, as well as first to be miniaturized enough to be used like this. And obviously there's cameras as well. I'll get into the cameras now. So here's a quick example of a drone survey we flew. This is looking for kimberlites somewhere in South Africa. This area is about 2.5 kilometers long by 1.5 kilometers wide and was full of culture. There were lots of power lines. That's what these white caps are. Farmhouses, mines, all sorts of nonsense. One of the great things about a drone is it gets you 20 meters off the ground or 10 meters off the ground, and it kind of filters out cultural noise. So for example, if I had to walk with a magnetometer in amongst an operating mine, I would get a lot of electrical noise. I'd pick up every truck, I'd pick up every shed. But I can actually say, well, in this particular case, on this survey, I want to fly about 20, 30 meters up. And just above these power lines, I'll cut out the noise from the power lines. And then I will filter out most of the buildings and most of the muck from the culture. And in a way, that's my first level of filtration, upward continuing, if you like, from a ground survey. The speed comes in here. 2.5 Ks by 1 Ks. Took us less than a day to fly this, 1 day to interpret it. And voila, you have your answer. Well, there's your kimberlite pipe. And there are a whole bunch of what we think are dikes coming through here, kimberlite dikes, which we could tell as different from all the dolerites in the area. Let me just go back. We said this is dolerite. That's a dolerite dike. This is probably a sill. There's some response from a sill here. That all just comes down to interpretation. But the bottom line is that within 2 days of putting the drone out there, you have fully fledged interpretation, the whole thing done, filtered, the lot. So it's much faster than a ground survey and it's less noisy. So that's an example of a real-life survey. What about the cameras, the LiDAR, the altimeters, the hyperspectral, all of that? Okay, here's an example of what we do with LiDAR on a drone. LiDAR are usually quite expensive. If you do it with an aircraft, much cheaper with a drone. What we can do is we now measure with the laser. LiDAR is laser interferometry, basically. This laser fires, again, something like 20,000 times a second, and it picks up every little blip in the terrain. So here we're doing a digital terrain model, essentially, but it can fire through leaves because it fires so often. Goes right through the leaves of the trees and everything, maps the ground. And then afterwards, because we're flying with a camera at the same time, we can essentially plaster the true color, the RGB coloring, on top of the relief. So now we have a 3-dimensional look at our landscape, where every tree and every building and every little digging and of course the workings, they all have a 3-dimensionality to them, and we can view them in 3D. I'll show you that now. But also we can put natural color onto them. So essentially, it's as if you're sitting on the drone looking down at it and you're seeing everything in color. We can also use reflectivity coloration on a LiDAR survey. So again, we have the digital terrain model, which is accurate to 1 or 2 centimeters. But we can say, right, the most reflective stuff will be red, the least reflective stuff will be blue, and everything in between. And sometimes that helps us filter out, say, the vegetation. Anything that's dark in this might be vegetation. Anything that's brightly colored in red may be what we're looking for, which could be silt or diamond digging in this case. And then what it's really useful for is measuring how much material has come out of a pit and how much material is standing in the tailings, or sorry, standing in the dumps. So every week, guys take stuff out of a pit and they plonk it on a dump as a sort of a, which they're going to access later. And by flying a LiDAR survey every week with a drone, you can literally say how much material came out of the pit and how much is now sitting on the dump. And you can view it all in 3D, and you can put the RGB coloring onto it. So you have your trees in natural color and you have the soil in natural color. So a lot of people like Palabora, for example, want to know how much magnetite is sitting at a dump and how much has been taken out by a truck and how much is added onto this dump, how much has been subtracted. You do a 1 centimeter accurate LiDAR survey every week, and every week you can say, well, the dump size reduced by this many centimeters cubed. So that's how much has been taken off the dump, and this is how much has been taken out of the pit and added to that dump. So what are the problems of drones? Is we have a line of sight rule and therefore limited range. Basically, most countries tell you that you have to be able to see the drone at any one point, so that if it goes down, you can see where it went down. It's a bit of a ridiculous rule, and we get away from it by putting ourselves up on a hill and using binoculars, or excuse me, you can literally put spotters out in your survey area or build platforms. Usually you try and use copies and try and view the drone that way. But it is a pain, particularly if you're in a flat area. Say you're in Botswana, you can only really see that drone for, if you're lucky, a couple of 100 meters at a time. So then you have to build a platform in the area, or it's just not realistic to fly 500 meters at a time. You want to try and fly blocks with a drone of 2 kilometers by 1 kilometer wide and then merge all the blocks together, something like that. It's also slow compared to an aircraft in terms of not speed, but production. So we can really do about 100 kilometers per day. Ground mag is about 10 kilometers per day. And using an aircraft like a crop sprayer, you could get up to 500 kilometers a day, even 700. So again, you can see we're right in between the ground make survey and the aircraft survey there. Power lines and trees are a problem. We have smacked trees in Angola, and we have put our drone and our bird into power lines. So one of the things you have to do before you do anything is fly a very accurate digital terrain model with LiDAR. Create your own digital terrain. In the software, tell it that it must drape this by 25 meters, which is the highest tree in the area, or you can use obstacle avoidance, which has forward-looking cameras. And when the drone sees something coming up like a tree, theoretically, it's able to go around it. But in practice, it doesn't always work. Power lines are a bit of a nightmare because you tend to catch the strings of the bird. The bird goes under, the drone goes over, and the strings go straight in. So we have nuked our drone a couple of times like that, and nobody will insure these things. It's literally impossible to get insurance. We have cross-border issues. Most governments want to pounce on drone surveys and say that they want to make money out of them, and then they start demanding civil aviation and military permits and blah, blah, blah. The whole thing becomes a nightmare of crossing borders. So drone surveys are not everything they're cracked up to be. We do have problems, lots of problems, and paperwork with pilots. Pilots have to be qualified. They have to do regular tests and pay money towards those tests. They have to have their paperwork with them, etc., etc. And you have to get permits whenever you fly a survey, particularly if you're near a military base or near an airport. Most countries will tell you may not be within 50 kilometers of an airport and maybe even 100 kilometers from a military base. And of course, the military loves to throw its weight around. They immediately ask you, do you know where the military bases are? You say, of course, I don't know where they are. They're all secret. And then they crap on you because you don't know where the military bases are. And then you have problems with the local population. Some of them get a bit upset when you're flying over with drones. Sometimes they throw things at them. Sometimes they try and shoot them down. One of the problems is, of course, that people associate drones with military activity, thanks to the US of A using drones to launch missiles, etc. Luckily, hexacopter drones don't look anything like their fixed-wing counterparts. One of the reasons we prefer hexacopter drones is that fixed-wing drones look very military, and hexacopter drones look more like toys, like the. So there are lots and lots of issues. And one of the problems is, of course, the weight of the instruments. You need a really big drone to lift 5 kilograms. So if I look at the drone developments that we're getting into now, of course, we're going to see a massive explosion in developments because everybody's starting to use these for various things. What we need is longer range. At the moment, we're using lithium polymer batteries, and you've got to have about 30 of them in the field, and you have to recharge them every 30 minutes. You have to have a full-on bucky there with fans and fridges and recharging facilities and shade and everything. And these batteries are like 2,500 Rand each, so you have to have a massive investment in batteries and be charging all the time and bringing the drone back to base after every half an hour, put new batteries in, take off you go. So then your issue is, can we use a hybrid fuel? Can we use fuel? Or can we use a hybrid which is using fuel and batteries? Problem with that is we have even more issues with fuel because governments fear that when the drone crashes, that the fuel is going to explode and you're going to start a fire. And if that's in an urban area, then you have massive problems. So we're looking rather at better, longer life and lighter batteries. And as we all know, that's happening all the time. We try cobalt, we try vanadium, we try lithium, and we just keep going. The other thing that's happening is we're getting tiny crystal packs made for radiometrics. Normally, crystal packs are very heavy. The sort of weight of a crystal pack you'd put in a normal aircraft for a MAGRAD survey is about 30 kgs. There's no ways you can carry that around with standard sort of drones. But up to 5 kilograms, maybe, we're starting to make crystal packs that come in very light, about 3 kgs. But the problem with those is they're not very good because the way it works with gamma rays is the bigger your surface area, the more accurate radiometric survey is. So that's in its infancy. We're going to get there as always. Most exciting thing I think that's happening is the B-field EM surveys using a loop on the ground and your fast sampling magnetometer. We're getting magnetometers, funny enough, it's ironic, but they're starting to use diamond magnetic sensors, diamond-based sensors, and they reckon they're going to sample at 20,000 hertz and even more. So we really are going to be able to start doing EM surveys with drones simply by flying a magnetometer. And if you tell me that you think your sulfides or whatever it is of interest are in this field, we just energize that with a loop and then we fly over it with a drone just like a mag survey. We're also getting electromagnetic and resistivity sensors miniaturized for drones. That's happening at the moment. I'm going to show you what one looks like. It's like something out of Star Wars. And then, of course, we're getting not just the LiDAR and the color cameras, but the multi and hyperspectral surveys using cameras in the shortwave infrared band and thermal bands, etc. So you can basically buy these things as cameras online. You can buy a hyperspectral camera online, put it on a drone, take a whole bunch of photographs, send it to Neil Pendock for processing. So all of this can be done. This is what a new EM, a small EM system is looking like. It truly is something out of Star Wars. There's a little loop on the bottom there. We have magnetic sensors. It's looking crazy. And obviously we can go much bigger than this. We can go to really big drones and then carry something slightly bigger than that. I'll show you what an AMT sensor looks like shortly, and then you'll see the kind of way we're going. We're making up small darts that can go beneath a drone like this. So say maybe no longer than a meter long, maybe 3 kilograms in size. So all sorts of developments in the drone world. Right, it's half an hour down. Just going to move on to some gravity quickly. Essentially, gravity plays a big role in diamond exploration simply because when we're in magnetic background, gravity's or EM is our next call to how can we spot a kimberlite. We use a differential GPS usually, and we use a centric gravimeter that looks something like that. And basically it works on the principle that two masses attract each other. Essentially the mass of rock beneath the gravimeter attracts a mass within the gravimeter, which is sitting inside a vacuum, which is super cooled sometimes, or just in a vacuum. It attracts it downwards if the rock is dense, or it lets it go up a little bit if the rock is not as dense as the background. So what does a gravimeter measure? It's essentially the gravitational attraction of the rock directly beneath it. Gravimeters are sensitive to variations of 1 part in 100 million, which is less than 10 ppb. So they're extremely sensitive instruments and very expensive. And in order for this to work, we need to know our relative elevation or our exact elevation to 2 to 3 centimeters. So huge steps were made the days when satellites started putting out accurate corrections to elevation. So we now use differential GPS radio. So we use GPS as the theodolite, if you like, and we use a correction from a base station or the dumpy level. So essentially it's all done with GPS, which is another great technological advancement. Why would you use gravity? Well, sometimes you have a magnetic background that is very, very busy and you can't spot your kimberlitic dipoles in it. That happens very often. For example, the mobile belt. Sometimes you want to confirm the size of a kimberlitic body. Sometimes only certain facies of a kimberlite are magnetic, and others are not so magnetic. So you get different pulses of magma. They don't have as much ilmenite. Maybe there's not as much iron in the ilmenite. So you have varying magnetic response across any given kimberlite. And by doing another kind of survey, like an EM survey or a gravity survey, we can come up with several sizes for the body and then average it, for example. You may suspect non-magnetic kimberlites. Group 2 kimberlites don't have a lot of ilmenite in them. They're very micaceous, and therefore you can fly an extremely sensitive magnetic survey in a quiet background and still not see them. I'm going to show you some examples of that from Angola. Note that a gravity survey is slow, and to cover a large area, it takes a lot of time. Airborne gravity is getting better each year, and we know that De Beers used a Zeppelin, and we know that you can now fly airborne gravity gradiometry with aircraft platforms, and it's starting to be used quite a lot in kimberlite exploration. The issue has always been the difficulty in measuring the aircraft movement accurately, because that's an acceleration, and the gravitational force is essentially acceleration. So you have to know exactly what your aircraft is doing. Hence, we use the gradients. It's much easier to work with gradients than total field. Simplified density structure of a kimberlite type is generally that the top 30 meters or so in any given weather terrain is less dense than the main body of the kimberlite beneath it, because it's weathered. So essentially we get yellow ground or crater facies on top. The density is down at approximately 2.3 grams per cc, and often the main body of the kimberlite, I'm sure we don't use these terms anymore. I've been out of De Beers for a while, but what we used to call TKB or hypabyssal kimberlite, is often more like 2.5 to 2.8 grams per cc. So we're looking for a little gentle density low on top of the kimberlite pipe, and if this is, say, quartzite, which is 2.7, it's going to stand out nicely as a low. So this is what we're expecting to see. Gravity profile comes in. You'll see how much bigger this gravity low is than the body. Really, the kimberlite sits in the middle, and we start getting a decrease on the sides. So again, we're going to have to do some fancy filtering to get a more accurate idea of the actual size. Some notes: if the density of the country rock is very low, the pipe can actually show, the kimberlite pipe can actually show as a gravity high. So it's essential to know what your background geology is, have a good handle on what its density might be. We're looking at a relative contrast, so you have to be aware of the surrounding geology. Here's an example from some kimberlites in Botswana, where you can see these two tiny little dipolar features here. So we're quite happy that these are magnetic dipoles and then maybe kimberlites. Now, maybe with gravity, we can tell which is a kimberlite and which is dolerite. You can see there is a lot of dolerite sill activity in the area. That's what all this other muck is in the background. First of all, I do a derivative on my magnetics. That tightens everything up. I see they're both nice little dipoles, but they look quite different. This one is more of a high. This one has a strong low. So what is that telling me? Well, let's do a gravity survey and see. If I just do a total field gravity, Buga gravity here, you can see how strongly it's picked up this huge doleritic body here, and this one here, the sill. And even in the total field, I can see there's a bit of a low, a little depression over that body, but nothing over that one. If anything, there's a slight high. If I just did, for example, a derivative to sharpen that up, or a residual, I would immediately see that there's a nice low over that body, and there's nothing over that body. So immediately I've discriminated between these two bodies. I'm thinking that this one is a kimberlite and that that one is not. I may be wrong. I mean, you may actually have two kinds of kimberlite in any given province. There's a big structure separating these two anyway. But my first indication as a prioritization tool is that the one with the gravity low on it is some sort of crater facies or weathered kimberlite, and this one is more likely to be doleritic. There's an example in Angola where in the total field magnetics, we don't have a classic dipole. We just have this strange looking magnetic high. I would not normally go for that as a kimberlitic target. Same with these things here. We don't really have strong lows with them, don't like it. And you get a lot of this, a lot of monopolar highs. We're not sure what they are. There's lots of dolerite in the area. There's lots of other muck. But in this case, indicator grains were telling us that this may be something. Let's do a gravity survey over it. And immediately we see this beautiful, strong gravity low. Drill two boreholes, and this one intersects a kimberlite. So it's a good discriminatory tool, and it's a good prioritization tool, and it's good for deciding whether you should drill something when you're not sure, or you may have lots of drill targets. So gravity is definitely a very, very powerful tool in our arsenal when it comes to kimberlite prospecting. Sometimes we have gravity highs and lows over a cluster of kimberlites. And the reason for that is that kimberlites pick up country rock. So when they intruded, they can sometimes pick up massive xenoliths of the country rock. That's something else to be aware of. So in this case, this is a kimberlite pipe. It's got a strong gravity high over it. It happens to be full of basalt, which is what the rest of this is. These two little kimberlites here in the cluster, these are all kimberlites, are little gravity lows, and those two are gravity highs. So it all depends on sometimes not only what the background is, but whether they picked up large blocks of xenolith. So you've got to be very careful. As always, geophysics, nothing is cut and dried. It's more of an art than a science, and experience counts for everything. You need to go, wow, I've seen this before. I've seen kimberlites that are highs and lows in some backgrounds. So that's gravity for you. And of course, now with Voxy again, we can do some potential field, just like magnetics. We can do 3D, three-dimensional modeling, and we can come up with bodies that start to look surprisingly realistic in terms of kimberlitic formation or kimberlite formation. In this case, it's the gravity has managed to split this kimberlite into two bodies and even two separate lobes. And we start to get an idea of what it might look like at depth. Of course, potential fields are not very good at modeling at depth or with depth extent, but it is a start, and you can use this to direct your drilling. Okay, moving swiftly along onto EM because we're running out of time. We've got 20 minutes left. Basically, with EM, we measure conductivity. Connected conductors give the strongest response. Generally best for metallic substances, things like sulfides, pyrite, etc. But in resistive terrain, weak conductors such as kimberlite can sometimes be seen with EM, and that's what we work towards. They're generally very weak conductors, but if the ground is very, very resistive, for example, in Canada, where you've got glaciated granitic terrain, then your kimberlites stand out nicely. And the reason they do that is because they have weathered ground. They have clays on top because they're weathered. When would you use EM? Magnetic background, again, very busy. Can't see my kimberlites because the mag is so busy. Again, I want to confirm the size of a body, or I want to detect, in the case of alluvials, the clay layers. Sometimes clay layers are useful when you're mining alluvials. Sometimes there's a clay layer just above what you're interested in terms of your gravel, or even within your gravel. Therefore, EM becomes quite a useful tool in mapping your channels. So channel mapping. And again, when you suspect a non-magnetic kimberlites present in an area, I'm going to show you a good example from Angola. Note that EM is quite expensive. It's more advanced. It's not as expensive as an airborne gravity survey, but it's a lot more expensive than an airborne magnetic survey. So as always, everything's relative. Can I afford to fly an EM survey? Can I afford to fly a gravity survey? If not, then I've got to do it on the ground, but I can't cover a lot of ground. So these things, everything's an interplay. It all depends on budgets. Basics of EM is essentially we fly over the ground, we pump a primary field into the ground, we turn it off, and then we have a receiver, and we measure the secondary field coming back from anything conductive. So we've set up an eddy current in this body. It creates a secondary field. We turn off this primary field quickly. We're talking about milliseconds, microseconds, and the receiver picks up the secondary field coming from that body. So we pump it into the ground, and then we get that guy coming back. Only reason it works sometimes over kimberlites is for the same reason it works over gravity sometimes. Nothing is a golden rule. Sometimes it works, sometimes it doesn't. Essentially, we have conductive weathered ground again, and we get serpentinized clays in here. And it's the formation of clay, essentially, that gives us free ions, which are therefore running in the ground, will run in the ground like electrons. And therefore, we have a weak conductor over some kimberlites. Sometimes we have crater facies over a kimberlite, and there are clays in the crater facies. So it all comes down to where are you and what sort of kimberlites do you have. As an example of 2 or 3 in Angola, these are magnetic dipoles. Looking at total field airborne magnetics here. There's a dipole, there's a dipole, there's a dipole, there's a dipole. But over here, there's nothing. We fly EM over that area. Just remember what this looks like and where that X is. And lo and behold, we pick up that magnetic dipole. But if I go back to this guy, you'll see there was just about nothing there in the mag. This is a good example of where we picked up magnetic facies of a pipe, elongated pipe, and there are the magnetic facies. But over here, we have a totally non-magnetic facies. And thanks to the EM, we're able to put a hole in there and say, wow, this pipe's much bigger than that mag body. In fact, the bulk of it is over here. In this case, probably crater. If you look at these 5 magnetic anomalies, they're all very, very different. This one you can hardly see. It's almost a texture. That's a classic dipole. It's a classic dipole. These are small dipoles. That's the total magnetic field. We fly over this area with EM. And, sorry, before I show you the EM, this is a horizontal gradient of the magnetics. Great thing about the horizontal gradient is it highlights the circular nature of the body. And in this case, in this area in Angola, it actually shows us multiple lobes. There are 3 sort of lobes of this guy. And sometimes in just one of these dipoles, we'll have, it looks like an outer crater and then something in the center. This guy just something in the center, maybe something out in the outer zone. So horizontal gradient is a very good filter in certain areas where you're looking for kimberlites. If I now fly the EM, and this is channel 25, so it's just one of the time gates, we're picking up the rivers very, very strongly. So all these rivers have clays in them, and essentially what you're looking at here is almost a topographic map, except that some of these bodies have lovely circular features on them. And you'll see there's an electromagnetic response in a circle, a donut around this body, but it's more resistive in the center. So what it's telling me is that we seem to have some sort of a conductive outer rim or crater, and then with at the center of this body, it's resistive. So maybe that's the kimberlite. These guys don't show at all. This guy's saying, heck, well, I've just got a bit of river sediment on top of me. That one shows a little bit of an electromagnetic high. This one shows two circular features with a river going through the middle. So you've got a host of different responses, just like you did in the mag. It's so useful to be able to view everything. Mag, EM, tau, channels, everything. We've got so many different responses. When I look at later channels, when I look at tau, which is the decay constant, and I can look at it for just say 6 channels. This is time gate 19 to 21 on the SkyTem system. You'll see that I've picked up the circular nature of that big body. Here I've picked up the central core there, which was a river, a body with a river going through it. I'm now getting a hint that there's something circular there, maybe a hint there, but essentially nothing, and then a river just passing through there. So again, 5 different responses. Well, let me just go back.
Totally different. 15 minutes.
Okay, I'll just have to speed it up a little bit. So basically what this is showing you is that EM can detect different kinds of kimberlites, different kinds of fascies, and totally different responses on different kinds of kimberlite. And but the interplay of the magnetics, the decay constant, and the different time gates, it becomes very useful. AMT, so this is something that is becoming more and more used throughout the exploration industry, audiomagnetic tellurics. It's basically a deep-seeing electromagnetic technique with the added benefit is that we don't need a transmitter. It basically measures the weak currents in the crust from lightning strikes. And a lot of these lightning strikes are up at the equator, say in Africa. All year round, we get lightning strikes at the equator, and then these very weak telluric currents come cruising back through the crust all the way down south or all the way up north. And we pick those up by listening with cables and with magnetometers for at least 20 minutes at any one point. And then we come up with ratios that show us the conductivity of the Earth beneath us. Essentially, it's a deep-seeing electromagnetic technique with the added bonus that we don't need a transmitter, lightning strikes or a transmitter. And this is it's not a new technique, but it's a technique that is being used more and more for kimberlites and indeed even for alluvial. Here's an example of a basalt layer in Botswana, where AMT, or in this case, controlled source electromagnetic tellurics was used. Controlled source means we actually put a cable in at infinity, so you can, in fact, add to the current. If there's very weak telluric currents, you can add, but we don't always do that. Often we don't. And you'll see there's a hole in the basalt here. So we're measuring resistive basalt, resistive basalt, resistive basalt. Suddenly there's a hole, and then more resistive basalt. And this is telling us where this kimberlite body is, and it's also showing us that there's shale or something more conductive, possibly even an aquifer beneath the basalt. Here's an example of the Regis kimberlite in Brazil, where an AMT section is done over the body. It's starting to show us, okay, now what we've done in this case is AMT essentially measures resistivity, not conductivity. So what we need to do is just flip it around. It's the inverse of resistivity. So all we do really in this image is we make the low resistivity values red, the hot colors, and the high resistivity values become the blue colors. So in other words, the kimberlite is more conductive than its surroundings. And that's what the Regis kimberlite looks like in section. But if you do multiple sections and you add them all together, you can do some very clever 3D modeling. And in fact, once you have it in this 3D shape, you can cut and slice and dice, just like you can with the other techniques I showed you in Boxy. You can slice and dice this kimberlite pipe, and you get something that looks quite kimberlitic, tapering off to a root down there. Because AMT is our deepest seeing technique, it can see down about 1 kilometer quite easily. The reason for that is we don't have to put the current down there. It's coming from the equator as lightning strikes or a nearby thunderstorm as a lightning strike, and it's automatically very deep. It's already 1 kilometer down. That's the beauty of AMT. Just by changing the frequency we listen at, we can convert it to depth. So we can image, theoretically, a kimberlite pipe like this Regis kimberlite pipe in Brazil. We can image it in 3D. Down to, in this case, this is 800 meters. And you can slice that, you can slice through it, and you can see we're getting a very realistic crater shape out of this AMT. We can slice it in plan, and we can view it in 3D, spin it around, and you'll see that down to the first few hundred meters, we're getting a very nice crater shape, classic champagne glass. So AMT is becoming massive. And I do know that there have been some very nice studies for masters and things to do with De Beers that unfortunately I wasn't allowed to show, that trialed numerous AMT techniques, because there are various ways of doing AMT, over a bunch of kimberlites in Botswana. And that paper should be coming out sometime. When it does, we'll look forward to it with anticipation, because some of the techniques managed to image these bodies in Botswana down to great depth. Mobile MT and ZTEM. Okay, these are the kind of birds the guys are making, and these are flown from helicopters at the moment. This is becoming very popular. People are now flying AMT from the air. You can either measure the magnetic field, or you can measure the electromagnetic field from these telluric currents, or both. And what you do is you measure them in the X, Y, and Z direction. That's why the bird is so round, because it has coils in 3 different planes, just like we sometimes do with EM. And you have base stations. You have something on the ground that measures the telluric current in the X direction, and something that measures in the Y direction. And then you use that base station on the ground, just like you do with a magnetometer or with a differential GPS, to modify what the aircraft is receiving. And therefore, you can map essentially deep conductors. This is the KL1 kimberlite north of Sudbury in Canada. This is a ZTEM survey over it. Actually, no, I think this is a mobile MT, which is, they're just slightly different systems. And not only are we imaging in plan, but we can image it in section. You can see what good resistive granite on both sides, and an idea that this thing is a kimberlite in section, just like we do with EM. Just remember, no transmitter required. So becoming very, very popular. And in fact, mobile MT is new. It's only just hit Southern Africa. And of course, again, we can do the classic kind of 3D modeling that I was telling you about. In this case, this is down to 800 meters. And this is done just in Geosoft. So things are heading our way in 3D in a big way. Ground penetrating radar, I'm going to cover in 5 minutes because I'm so running out of time. But essentially, we're just looking for reflectors. Again, it's an electromagnetic technique. The reflectors look parabolic, like you can see in this image over here, but we migrate them to get rid of this time adjustment over here, and we get horizontal layers. And we get, what we're looking for is deep seeing geological information at 40 megahertz. None of the shallow stuff that maps roads and pipes. We want to go under 100 megahertz down to 40. So you have a long antenna, 2 to 3 meters long, and you can carry it. It's air coupled, and you want to work in rough terrain. So that's what we're looking for when it comes to kimberlites and alluvials. This is what we want to be able to do. This is really very rare to see something like this, but this is down to 70 meters that we are mapping the edge of the basin. We're mapping sediments in the basin. We're mapping an incredible amount of information. Don't get your hopes up. This is only on very rare occasions that we see stuff like this. Here's a real life survey done by Mike Shaw for diamond alluvials using our equipment. He did this himself. This is the Gobos River Valley in the Cape. He wasn't actually looking for alluvials right here. He was just testing it. That's what the river looks like. And you can see that here is the base of the river channel here. Get all this muck on surface, the reflectors close to surface, related to ground effect, etc. But you can clearly see down at 10 meters, down to 15 meters there, the base of the Gobos River channel, and that's the rising bedrock surface there. This is a river channel that is seen underneath Kalahari sand. This is an alluvial diamond study, again done by Mike. And I think this is fantastic because it's done under sand, and you can see the channel over here quite clearly. So we're starting to get somewhere with deep seeing antennas in radar. And we're starting to see through Kalahari sand. And in fact, we believe that we were seeing down to approximately 10 meters over here. Again done by Mike. This paleo channel is down at 10 meters depth. And this is over a large area. So this is 300 meters wide, the section you're looking at here. So that's 200 meters long, 20 meters deep, that entire gray section. And there's 5 meters of sand on top. And you can see that as long as you're not looking at a small area where you don't know what's going on, once you put this all together over hundreds of meters, you can see, in fact, you are mapping a paleo channel, which is very nice. Thanks to Mike Shaw for that. And a mafic sill, also buried under sand. I'm just showing you this section here in the bottom gray image. So I've taken these 2 red lines and I've blown it up. And down here, you can see we're going along beneath the sand, 7 meters beneath sand. And suddenly we get these reflectors coming down to 12 meters here. And that's a mafic soil, which we believe to be diamond bearing underneath Kalahari sand. So ground penetrating radar, no, it cannot be used on a drone unless the drone is like a foot above the ground. We still don't have GPR that can couple in the air for meters. And just quickly in the last 5 minutes, stuff we can do with geophysical logging. In kimberlite pipes, this is some work I was involved with De Beers many, many years ago. And guys like Bill who are watching this will remember it well. Essentially, you throw probes down a hole in a kimberlite pipe, and you measure these things: density, porosity, magnetic sus, gamma, neutron porosity, resistivity. You measure all of those things up on surface by throwing the probe down the hole and slowly bringing it up. It measures them in the sidewall of the hole. And essentially, you can typify the types of kimberlite and the types of xenolith you have in the pipe. This is neutron counts on the y-axis and gamma counts on the x-axis on a log scale. And we start to typify what sandstone's response is, what this basalt response is, what that is, and also all these different facies of kimberlite. How do we do that? I'm going to show you how. This is what the results is like. Down the hole, 3 different holes, drilled close to each other for comparison. Got superb results, 3 different holes giving a very, very similar look at a kimberlite pipe. The top 80 meters, the green stuff is kimberlite. There's a basalt block in the kimberlite. So this is a scale of 0 to 100% across each hole here, i.e. there's 90% kimberlite where you see it green, 10% basalt where it's got a bit of red, and then where it's all red, that's 100% basalt. So for 80 meters, we're going through kimberlite, and then suddenly you hit basalt. Down here, we hit sandstone. Down here, we hit a bit of mudstone. It's telling us exactly how much kimberlite we've got at any depth, 90%, 85%, 80%, etc., and how much xenolith material there is every 10 centimeters, essentially. So a very powerful tool to calculate the dilution or ore dilution in the kimberlite body. How do we do that?
3 to 4 minutes, Gavin.
Okay, well, I'm basically wrapping up. I just need another minute. And we do that by measuring all these tools down hole, and then we plot them, we cross-plot them. Resistivity against neutron. Here are all your xenoliths, pulls them out beautifully. The yellow one is sandstone, the pink, the magenta one is one kind of basalt, the blue one's another kind of basalt. And here are all your different kimberlite types. They vary in conductivity or resistivity. There's kimberlite 3, 4, 5, and 6. And we can then take these graphs, create a mixing line between here and xenoliths over there. So these are mudstones and basalts, and these are sandstones. And we create a mixing line, and we can unmix it. We can say when we have 400 counts per second of neutron, that's 100% basalt. When we have 900 counts per second neutron, that's 100% of this kimberlite, and we unmix that thing. That's how we create those percentages. And even more so, we do a ternary plot where I can tell you when you're 100% kimberlite 6, because density versus gamma is plotting in this zone, just like we do with minerals in solid solution series. Kimberlite 2, 100% of it has this density and that gamma count, and all your xenoliths over there. And therefore, come back to this plot over here, where we typify sandstone, mudstone, basalt. We start by typifying it in a known hole, and then we tell it, unmix it, and the software just unmixes it for us and shows us exactly what we've got down hole. So essentially, you are logging the hole, in this case, an RC hole, so very difficult to log, no core. It's just from chips. It's telling you exactly what percentage you have of basalt and kimberlite at any one point. Essentially, that's what we do with these unmixing relationships. Thank you very much. That's the end of it.
Thank you very much, Gavin. That was a very good overview of a whole bouquet of products. I guess a lot of the stuff is pretty new. We've got time for maybe just one query. There's one question in the chat box. When do you see a time when you can do 5x5 kilometer magnetic surveys with a drone? Is that far off?
No, we're already doing them. We're doing much bigger surveys than that. We just survey them in blocks. So I can do any size survey. We can do, I think we're doing one now in Swaziland that is that size. It's at least 5x5. But what we do is we divide it up into blocks, line of sight blocks, and also radio link blocks. So you can't lose radio link with a drone. So you go up on a hill, you say, okay, how far can I see? And then you have this very clever software that you show it where you are, and it plots line of sight for you and everything, and then it draws a block for you. It comes in GSOFT. It's called the drone. It's a drone module, and it tells you you can fly this block from this hill. So then the only difficult part is the processing. We need to merge those blocks seamlessly, and obviously there can be trouble there. But again, we fly tie lines, so you basically take the tie line and you do tie line living with those blocks. So we can do any size survey. It just once you get to a certain size, it becomes more economical to fly it with an aircraft rather than a drone.
Okay, the day before yesterday, Hannes Viljoen introduced the concept of cratons while he was talking about diamonds. And he also mentioned Clifford's rule, which has been one of the staples for area selection in diamond exploration for a long time. And Clifford's rule was, of course, established long before we had any kimberlite dates. We didn't know that all these rocks that in these metallogenic provinces that he was looking at, the shields of Southern Africa, that they were actually Archean. So, but later on, people found out more about dates of kimberlites, of country rock and diamonds. And we now know that primary diamond deposits tend to occur at Archean cratons. What I want to talk about is the fact that not all cratons are born equal. And we have, just a minute now, why don't I get my, oh, here we are. Not all cratons are born equal, and some have diamonds, some don't. And so what I want to do, I want to discuss the two. I initially said I was going to discuss the Slave province, but I will add the Superior province to it and compare this to the Kapval craton, which of course is the type example of a diamondiferous craton. Then afterwards, I will derive some general conclusions about Clifford's rule and exploration strategies. You can see here, mines are very unevenly distributed in the world. There's Siberia on the, maybe I should take a different pointer, huh? Pointer options later. Here is Siberia. Then of course, Southern Africa here. There is a bit more now up here in the Baltic field, in the Arkhangelsk area. But then there are the new areas here in Canada, the Slave province and the big Superior province here, down here, where we have also now 2 diamond mines. Okay, most cratons can be described in what I refer to as the life cycle of what I call the life cycle of diamondiferous cratons. It starts out whenever we have, where we have a diamond mine that is at least the ones that have behaved like the ones in the Kapval craton. We start with the earliest continental nuclei, which have P-type, this is peridotite Hartsbergite type diamonds, and they are old. Then, and they are probably worldwide. And as soon as we come later into the Archean, down here I have shown, this is the P-type diamond way down in the time scale in the Mesoarchean, Periarchean boundary here. The stage 2, after we have these diamonds there, usually nuclei can combine, the early nuclei, and there are the first E-type diamonds formed, and any peridotitic diamond that forms later is usually a lherzolite. Now, the end of the Archean, around 2.5 billion years, is usually the cratonization of the of most cratons. Kapal is different, as we will talk about. After these first diamonds are formed, it's usually a question of survival for the diamonds in the mantle root. There are more diamonds added, E-types and lersilytic types, but it's more because cratons break up, they get involved in younger orogenies. They are surrounded by various Proterozoic mountain belts and so forth. So we have to figure out when we look at a craton and then analyze it, what are the processes there that try to destroy the diamond, the different mantle roots. And then, of course, at some time, the kimberlite is intruded, and or kimberlites are intruded. There can be several sets, of course, and that is usually younger than 1.8. And well, the oldest that is a good mine is the Premier mine or the Cullinan mine, 1.2 or so. And so, and this goes, of course, can be as young as the Eocene, as we have certain pipes in the Lac de Grand field in the Slave Province. At that time, we might have, or shortly before the kimberlite eruption, we often have fibrous growth, overgrowth, or fibrous cubes forming by themselves. Then we might have megacrisp-related diamonds. And at that time, of course, the sublithospheric diamonds will be introduced as well, although they are then probably older and they come from deeper. And the final thing is, after the emplacement of the pipe, we have to worry about where the pipes are preserved and how the indicator minerals are dispersed. We won't go much into that. Okay, it all starts out with that early event that I was talking about. This is a uniquely Archean event, and it was, of course, recognized in South Africa. The seminal reference there is the Boyden-Gurney 1986 reference, Diamonds in the African Lithosphere, where they have studied all the garnets that come out of kimberlites. And in the diagram at the upper left, you can see the Kapal craton here. Every pipe there has subcalcic garnets. There is the edge of Zimbabwe, this must be Orapa and so on. And then off craton, you do not find these kinds of garnets, as you can see. And there's a cross-section that has been drawn from East Griqualand all the way to Laurentia in Namibia, in fact, right across Southern Africa. And here you can see what became the type example of a lithospheric root. These are the xenoliths that come in diamonds, of course, that come from below the diamond graphite inversion curve and up to the bottom of the lithosphere. That's really what we're looking for in a diamondiferous craton, a deep root with hard sphagitic and depleted rocks in them. And the inclusions of diamonds, here, this is a diagram from 1993, they show, of course, that the garnets that are included in diamonds are very subcalcic. This is heavily biased here by Finch, but nevertheless, you can see that here is the famous 85% line of John Gurney's. Essentially, separating lersilite and hartsfagate. The ages, of course, we know now much more about ages of diamonds, and when you compare them on different cratons, you can really see that if there are diamond mines, the early event is 3.2 to 3.5 event. With the hartspagitic diamonds goes worldwide. There are they're rarely even the exceptional mines like Australia, Argyle, you can recognize in the mantle sample remnants of an early mantle that was hard spaghetic. Now, when it comes after that, we have all kinds of different dates. Okay, sometimes a lot of events here, like in Southern Africa. We have lamproites forming in Premier. We have them in Forcefoot. There was a recent paper by Karen Smith, who has discovered the Forcefoot lerzulitic diamonds. They are probably related to, which event was that? Oh yeah, that was the 2.7. And what's the 2.7 in South Africa, and the famous green lavas that are all around Kimberley. Then the Forcefoot here, that was the Ungaluk lavas. I will come back to that. I might remember. But now when you see the Slave Province here, you see only one later diamond event, an E-type event. You can see lamproites that have diamonds. In the Superior, we have two ended. We have some that are here and questionable. We haven't got nearly as many dates, of course. And then recently, the Victor mine, where we found out that most of these diamonds are 0.72 giga-ann, so they are in late Precambrian, in other words. And that is, there are some very different processes going on, and I want to talk about those. Okay, then we have various detrital diamonds coming in, which I will also talk about, because it used to be for a long time that people just simply could not believe that diamonds are that old. And that today, still, people don't have any trust in the ages of inclusion, of dated mineral inclusions from diamonds. But we do have several places where we have detrital diamonds, 2.96 billion years old in the Slave now, and of course the famous Witwatersrand diamonds, which are 2.85 billion years old. So with that introduction, let's go into the two cratons from North America, the Slave Province and the Superior Province. The Slave Province is up here in that yellow circle, and the Superior Province is here on the southeastern part of the shield. You can see that all these Archean parts there in red, some of them are reworked Archean parts in the Proterozoic, like the Churchill Province. But then there are also Proterozoic mobile belts surrounding them here on the Slave Province, and here the Trans-Hudson belt that goes right across or around the Superior Province. And here, of course, in the Grenville bounding the Superior Craton on the bottom. Zeroing in on the Slave Province itself, you can see the Slave Province there surrounded by the mobile belts. And let me just bring out some of the questions that we want to ask. We want to look at briefly at the tectonic setting, and the geological setting. Then where are the kimberlites? We want to find where are the diamonds, which kimberlites are diamonds, and what are the diamond ages? How did they form? That's not all that clear, but that would be an interesting thing to find out. Where and how did they survive, the diamonds? What was the role of Paleoproterozoic intrusions? The Canadian Shield is shot through with diamond dikes and intrusions, and if they influence the survival of these diamondiferous roots? Are there the regional faults, the role of the regional faults? Then in the Slave Province specifically, the role of the Mackenzie plume. And we can also briefly talk about the controls of kimberlite volcanism in this part of the world. Here is the slave province just by itself. You can see here all the geology. This is essentially a granite greenstone terrain where some parts of the, I should say, essentially a Neo-Archean granite greenstone terrain where some parts, and you can see here these violet or these purple parts, has a basement. There's a basement terrain here, which we call the central slave superterrain. You can see it here without the geology in this right diagram. And it is characterized, all the sulfides in the primary sulfide bearing rocks, like massive sulfide deposits and so on, they have evolved lead isotopes. So they show that there was a basement present. The rest of the areas around this are accreted terrains. You can see them here on the eastern side of the central slave superterrain, the contoidal terrain, the Hackett River terrain, Council terrain, and there is here a small one that's called the Snare terrain on the west side. And these are juvenile Archean, Neo-Archean rocks. Now the kimberlites you can see all the black symbols here are kimberlites. Most of the kimberlites occurred throughout here, which is the contoidal terrain. But we know that this contoidal and the capsule terrain, that they are allothenous on the basement of the central slave superterrain. So there are Neo-Archean rocks thrust over Mesoarchean to Paleoarchean rocks. And we know the kimberlites that come through here actually have xenoliths of this 3.2 billion years up to that age. Okay, let's go next. And this is a diagram. If I go back here, this goes right across these different terrains, and you see the stylized stratigraphic, stylized stratigraphic columns, and you can see that the central superterrain, central slave superterrain has a basement, and all the other rocks are Neo-Archean. And just to give you an idea of what they're like, the central slave superterrain oldest part is actually on the margin of the province. It's the cast and ice complex, which has rocks up to 4 billion years old, some of the oldest rocks in the world. The next, this basement in many parts, wherever one sees it outcropping and where it's not too badly reworked, has a quartzite sequence, which is referred to as the central slave cover group. You can see here the unconformity of that quartzite on basement rocks. And you can see here some of the cross-bedding in the quartzite. So a very mature sediment, which, as we have figured out, is quite equivalent, although it's very much less, we have far less of it. It's like the Witwatersrand Rand sequence. It has the same age, it's 2.9. In this particular case, it ranges from 2.96 to 2.85. And that is now overlain either tectonically, and that's a big argument amongst the geologists, by Neo-Archean rocks here, the pillowed flows, and that's in the central. That's where you can see in the center here, that's probably that age. These volcanic rocks, they're 2.72 and slightly younger. Then they're overlain by turbidites, and that is again unconformably overlain by a polymictic conglomerate, which is up here in this. And the entire sequence is deformed. and the early Precambrian rocks here are redeformed together with this Neo-Archean sequence. And at the end of it all, at the end of the Archean, 2.6 to 2.58, we have enormous amounts of granites, which is referred to as a granite bloom. So that is the geologic setting in a nutshell. And now, where are the kimberlites? We have so far, the province has been pretty well explored, although there are many, many more mines to find as far as I'm concerned. But a lot of kimberlites have been discovered, and they are basically subdivided into 5 fields. And that's the lac de Gras field, where the Ekati and Diavik mines are, which is late Cretaceous to early Tertiary in age, 75 to 45 million years old, some of the youngest kimberlite pipes. Then there's Jurassic pipes here in the Jericho field. There was one mine, the Jericho mine in there. In the Southern Slave Province, which is Cambrian, 530, there's 2 mines, the Snap Lake and the Guachuque. And then there are 2 fields here, the Coronation Field, which is latest Precambrian, 630. 13 is the only number we have, 613 million years of age, which is Ediacaran. And this one here, the Western Slave, is Ordovician Silurian in age. Now I've drawn this line here, which is a very prominent fault, the so-called Vinaya fault that goes through here. And all diamond mines are to the east of it. There are kimberlites to the west of it. And the kimberlites are still in the Central Slave superterrane. So all kimberlites are related to this basement here and to the parts of the basement that are covered by the Neo-Archean allothenous rocks that lie on top of it here on this side. But diamonds are restricted to the west side, where this terrain is deeply covered by the Neo-Archean rocks. I will show you sections about that later on. Just an example, this is the first pit that was mined, the Panda pit. There's about this picture of the diamonds there. I took that on that was exhibited in the Ekati office, and that's 10,800 carats. And at that time, this was taken, I think, in 2004. And at that time, that was 1 day's production of that mine. So there's small pipes, but rich pipes. In the grades are carats per ton rather than 100 carats per ton. The carats per 100 tons. The pipes are quite unusual. They're different. They're smaller, much smaller than the Southern African types. They're essentially big holes blown into the country rock, or most often granitic rocks. And the kimberlite infill is pyroclastic and resedimented pyroclastic. Only the Cambrian kimberlites that we have in the southeastern part of the slave print are more like the Southern African ones. And this is a figure from Scott Smith. It has root zone and it has definitely a diatreme type facies. And this is the part that is preserved. So the pipes are slightly different, and the mines consist of smaller pipes, but several pipes each time. And so the overall resources are quite high in many of them. The best example here is the Koala pit. That gives you an idea of the size. They're all they range from 3 hectares to about 17 hectares surface area. They are steep walled. Here you can see the horizontal infill. And here you can see a sample of this is almost like an olivine sand with garnets in it. And the diamonds from that pipe look quite pretty. And these are just covered with very thin fibrous coatings. One particular one very interesting part is that these pipes contain wood. The resedimented, the kimberlites obviously were intruded into a swampy terrain where there were lots of trees, mainly sequoia type trees. And here you can see the largest wood fragment that was found in the misery pipe. There is the light switch, and this is a normal door, so that is a real part of a stem. As you can see, there is another tree stem right there. And on a field trip once, I think it was the IKC in 2003, yeah, people didn't believe that this was actually wood. So I had brought a lighter along, and you can't see the smoke coming up, but you can see here there's ashes, and the wood actually burns. You can take it out of the outcrop and burn it. So that shows that the infilling was from these swampy trees. There were fish and turtle fossils swarmed in as well. So it is a very interesting kind of assemblage. So that's the kimberlites. Now, where are the diamonds in terms of age, and where do they fit into the scale? They definitely, the lactigraph pipes and the ones in the southern part have all kinds of hard spaghetic diamonds, and they have been dated in two places it's about 3.5 gigaton. Then, instead of having early, there's no Archean E-types to speak of been found, but a lot of E-type diamonds and garnets and eclodites are approximately 1.86 billion years old. They came much later, in other words, post-Archean. Then, of course, I've put the kimberlites here on the right. That is what we call the kimberlite barcode of it. It's the 5 generations. And each one may have diamonds. All of them do have diamonds, and in some of them, they haven't really survived very much, but all have an original remnant of these hard spaghetic diamonds. And people, of course, have doubted the age of these kimberlites, of these diamonds, being 3.5 billion years old and then surviving under a Neo-Archean greenstone belt sequence that was too hard to swallow for many people. But already quite a while ago, we had found the survey had studied some of this cover group sequence, which is here. There's the basement, and there's this quartzitic cover group, and there's some small diamonds in it. And unfortunately, early diamonds got lost, but very recently, the people from the University of Alberta, with Graham Pearson, resampled this rock. They found diamonds in it. So we now know there are detrital diamonds in that. So all the greenstone belt sequences in Neo-Archean greenstone belts, we have already detrital diamonds in the sequence, very much like in South Africa in the Witwatersrand. There is one more thing that comes here. We have also in the Archean, in the Neo-Archean itself, we have lamproites dikes that are also, some of them also have microdiamonds. Here's just to show you, that's what that quartzite conglomerate looked like in the cover sequence that has these diamonds in them. There, that's where the diamonds are. And here you can see where the zircons that are the detrital zircons that are dated. The upper intercept here is 2 for this particular bunch is 2,935 million years, plus or minus a bit. So they're old diamonds there, predating the Neo-Archean greenstone belts. Now, this dike that I was talking about, this is John Armstrong standing near Yellowknife, near one of those dikes. And when you go and look at this particular sample, there's a bunch of xenoliths in there, and they have been known for quite a while. They are 3.2 billion years old, so they sit underneath the Neo-Archean deformed rocks, and they have 3.2 billion year ages. They have been checked several times here. And this dike is known to have some microdiamonds. Not much, but you can get consistently microdiamonds out of it. So the model of the Archean evolution is of the province is quite simple. We had an early terrain that was Paleum to Mesoarchean that rifted apart. Here you can see that we don't know where this piece went. It's absolutely not, has not been found, but it must have had a P-type root. And the next stage then, after the rifting, we had all these Neo-Archean terrains form, and they then amalgamated. Here is the Hackett River Arch. There's an arc, and there is a central volcanic belt arc, and there is a snare arc, and so on. And they then all amalgamated in the lower diagram. And that was followed. It's all together, and you can see here these Neo-Archean rocks over top of the Mesoarchean basement, and that's where the kimberlites, with the diamonds, are. So here is the diamondiferous root, and it's best preserved in the eastern part of that central slate superterrane, where it's covered by these rocks. Now, the E-type diamonds, which are more common in the Jericho kimberlites, the Jurassic kimberlites, but also present in the Ekati and Diavik mine, they came with a huge slab that was subducted from the west underneath the Slave province. The first sections that we had, these are, that's a mixture of reflection seismic with teleseismic here, and people had argued for a long time how old these various slabs that go under this. We can trace them all the way back to an 1800 million year Fort Smith terrain. And recently, this was lithoprobed by 2005. In 2010, Oedi and Close made they reprocessed this section, and they used crooked line acquisition so that they could have a three-dimensional picture, and they came up with this wonderful slab that goes down there. And that fits into here, and that means this part here is part of that slab going down, because there comes right to there, and it's about the right depth, 110, 120 kilometers. So that's where the interface of the old basement to the top and the young understrusted slab is, and that's where the E-type diamonds are related to it. When we summarize all that, we have an asymmetric part of the basement part here, and that's where the P-type diamonds sit in, and we have the Proterozoic rocks going underneath. We don't really exactly know what's happening in the eastern part. All we know is that the eastern terrains were overthrust here because we can see the xenoliths in the kimberlites that sit in the juvenile terrains. So we know that's allochthonous on top of it, but we don't know precisely what's going on here. So the E-type diamonds, they came, oh, sorry, there's first all that Neo-Archean activity, and there's this massive granite bloom related to it. And there are base metal deposits with it, and there are gold deposits with it. And then the next step in it was that the E-type diamonds went underneath. And you can then, in other words, say that this Paleo to Mesoarchean mantle route was actually totally underplated by these E-type rocks. And in fact, the Proterozoic slab underneath the depleted keel protected that keel from being eroded thermally or tectonically further. So I better go move on. Then the kimberlites came through. We can see the western kimberlites don't have any diamonds because much of that route was already eroded by the Proterozoic events. But here, these kimberlites have the diamonds. Okay, now the role of the Proterozoic intrusions, the dikes, in either controlling emplacement or causing deterioration of the mantle route. What I've done here is this part of the stratigraphic sequence. That's the barcode for the Paleoproterozoic dikes forms. They're mainly related to rifting within the province and so on. And here they are, here you can see them in spatial context. It's the same dike swarms. Here's the entire province. This is where most of the kimberlites are. And the one dike swarm that seems to have a relationship, or that the kimberlites may have followed in some fashion, is this one, the Lac de Gras swarm, which has some of the mines controlled along it. I show it in a second. There were other intrusions here, alkali complexes, and they have probably metasomatized this part of the mantle route, which was also tectonically eroded. So that's where there are no diamonds here, and that's where there's diamonds surviving in this part of the world. This is the picture just to show you that dike swarm, the Lac de Gras corridor, that is. It has 1, 2, 3 mines along it. That's the Cambrian mine, Snap Lake, and the Cati and the Diamig mine here. And you can see these are the pipes that are known of the Lac de Gras kimberlite field. And there are that's where the Cati mine is, and that's where the corridor of the Diamig mine is. They're about 2 million. One is 55 million years old, and one is 53 million years old, and each one has several pipes along that strike. Faults don't play a great role, except one here. These are all Proterozoic faults, and these are the dikes again, but these are all the faults that have been mapped, major faults. And most of those are related to the Proterozoic deformation and of the Slate province when it was indenting this area here. But there are some Archean faults that have been remobilized, and amongst them is this important one here, that all the diamonds are staying, diamondiferous pipes are on this side. And that fault, actually, the Proterozoic reactivation part of that fault zone crops out, and the fault zone itself has a lot of the late Archean conglomerates along it, here in this one, in this particular one. And the recent, I should say recent, I mean the Paleoproterozoic displacement is about 15 kilometers long, and it's an oblique slip. Here is the western side of that fault corridor, which is the west, which is also a Proterozoic fault, but following an earlier Archean fault, the Yellowknife Fault Zone. And they are very prominent, and that's on the pictures right there. So that's where still kimberlites occur, but they don't have diamonds to speak of. And on the west side, on the east side of this one, that's where the mines are. Now, the major event that affected the province was the Mackenzie plume, which intruded, which was probably the center of the plume was here. And here we can see a study that was done by Richard Ernst and Berger. The dikes intruded vertically here and then horizontally in this part of the world. So the circle of 500 kilometers around the radius here, the dikes started to go from vertical to horizontal, and that is where the diamonds survive, up here in the northern part of the Slave Province. There is very little in terms of, this is the circle here now. And
Herb, you've got about 15 minutes. Yes,
I have to move a lot faster. Okay, that's where the diamonds are gone in this part of the world. In Jericho, Jericho was mined, but it wasn't very rich mine. It's not mined anymore. And this is where all the diamonds happily survived. Okay, so let me go further. Let me go to the Superior Province briefly. The Superior Province is much bigger. It is also surrounded by Proterozoic belts, as you can see here. And the size difference, that's the Slave Province there up on the upper left. And the Slave Province fits into this part of the Superior Province quite comfortably here when you turn it around a bit to the right. So the province, the size difference is profound. And here I come to a bit of a comparison. We know, for instance, the Slave Province has only about 200,000 square kilometers. That's 10 to the 5 up there. The Kappa Craton, 1.2, 10 to the 6. So this is over 1 million square kilometers. The Superior Province has 1.57. It's even bigger. But you can see that when we compare the Slave Province and the Superior Province here, the greenstone sequences are these, and this is the basement terrains. While there was a lot of Archean, Neo-Archean activity going on, the Ventersdorf volcanics were intruded here, and they simply stitched the eastern and western part of the Kappa Craton. So they were already, the cratonization of the Kappa Craton happened here with Waters Rand, with detrital diamonds, right? And that's the basement. Whereas the other cratons, the Zimbabwe included, Superior and Slave, have a lot of Neo-Archean overprint over this. But the Neo-Archean rocks don't generally have many, the kimberlites in those parts don't show the depleted, the subcalcic garnets. So let's go further. This was what happened in the Superior, in the Kappa Craton. We have the eastern part coming under the western part, the Kimberley block, and each one had their own P-type diamonds, and that's probably the 2.9 event that showed the first eclogitic ones. And then on top of it, we have the earliest Witwatersrand Rand diamonds that are preserved. So definitely Archean, but all Meso to Paleo-Archean, Paleo to Mesoarchean. Here in the Superior province, we also have detrital diamonds, but they're in the much later conglomerates. This is a 2.7 conglomerate here in the Wawa Greenstone Belt, for instance. The Superior province youngs from the north to the south, and in this part here, we have 3.0 to 3.8 billion year rocks, and they get younger downwards, but there are older terrains interspersed here in this southern part. So when you see the same diagram that I drew for the Slave province, here are all the greenstone terrains, the Neo-Archean, these are all the basements. You can see there are a few that have basement terrains, but only a few of these basement terrains are rather big. The Hudson's Bay terrain here and the Hudson's Bay terrain there, that is where the diamondiferous kimberlites are. And here, this is where the detrital diamonds first came up to the surface. That's how the whole province came together, amalgamated from south to north. And this is where the diamondiferous kimberlites are. That is Renard, and this is Victor. And this is one of these older terrains that gets swamped in there. There's another one of these older terrains. So the old terrains are all concentrated in the north, and there isn't much in terms of diamonds to the south. Here are a bunch of sections that show, the lithoprobe sections show the remnants of subduction zones. That's in the eastern part of the province, and this is in the western Superior. There are actually two suture zones. Here are the old rocks. There are the old rocks, and there's all the younger rocks. Here are the diamond mines, the two, Renard and Victor. Victor is rather interesting because the Victor diamonds are 720 million years old, and that has surprised a lot of people. So let me just go through that. This is here in the Atawapas Cap Kimberlite Field, 0.72 billion years, gigahan. And that shows the Victor kimberlite, or one of the Victor kimberlites is like this. This is not the actual Victor itself, that's the U2 pipe, the Jurassic pipe, and there's an older generation nearby that is overlain by a lot of Paleozoic rocks, whereas this one has penetrated the Paleozoic rocks. You see the T1 is this one here on that one, and the U2 is that one. So they're very close together. And the students, Thomas Stachel and the students have figured this out. I will go past this one. The Kyle Lake, the T1 pipe, look at this. They have a lot of subcalcic garnets, whereas the Victor, which is wonderful diamonds, doesn't have any. So it has a few hard spaghetic diamonds when you look at the plots of the actual pipe, but mainly they are all like this. And the inclusions in the diamonds are Lurzolytic, and they're 720 million years old. So it's one of these rare cases. It's a bit like the Bushveld, when in intrusion, and this was the Kivanovan event in the central Superior province, when that heated up. This is the original diamond situation that was heated up. All the diamonds got destroyed, and it cooled down, and it came back afterwards, and it formed beautiful, very, very pretty and very expensive, $550 per carat diamonds of the Victor mine. So it shows you that not everything is straightforward. There can be late diamond forming events, and it pays to also take heed of the Lurzolytic garnets in the exploration. So I won't go through the others here. I will just sort of finish with my, oh yeah, just in the southern part of the province, Kirkland Lake kimberlites, and there is absolutely zilch in the depleted garnet field here. There's nothing there. And there's two reasons for that. One is, well, it has a hot geotherm, as you can see here on this side, compared to the Atawapiskat, which was a reestablished normal geotherm after the diamonds, or when the diamonds were formed. But there's also a huge dike swarm here, which is centered here somewhere. The Kirkland Lake kimberlites are right there, so they would be right in the influence of this plume, which was the Metashwan plume, 2.45 billion years old. And in addition to that, it's in the Neo-Archean, terrain, which doesn't have much of a mantle root left. So I probably should wrap it up right here. The term Archean craton has different meanings when referring to the Kapwa craton and the Slave Province, Superior Province of the Canadian Shield. The former is Paleo to Mesoarchean, and all parts are diamond prospective. In other words, that's why we saw all these, not every part is diamonds, but they all have subcalcic garnets throughout. The activity, all the overprinting granite blooms are all old, the Archean. You know, the Johannesburg granite is somewhere around 3 billion, if I remember right. So in the Slave and Superior Province, there was much Neo-Archean activity, and only the pre-Neo-Archean nuclei are really diamond prospective. So an Archean craton here means that you have to go, the Clifford's rule should actually say not Archean cratons, but it should say where there are Mesoarchean roots to the craton, and not the Neo-Archean parts. They are not, at least in the Slave Province, and in most parts of the Superior Province, they're not diamond prospective at all. And so, yeah, that's essentially all I have to say here. And there's maybe some time for discussion. Thank you very much.
Thank you, Herb. That was a very well illustrated and comprehensive talk. I learned quite a bit from it about the slave that I didn't know before. We do have some time for some questions or
Sure. Yeah. Should I unshare or?
Yeah, I think you could do. Yeah.
How do I do that?
There should be a green button that should say, there you go. You managed it. Herb, you didn't say anything at all about the Churchill province. Is anything going on in the Churchill? And
there are kimberlites in the Churchill province, and there are also older parts in it. I didn't say anything about it simply because there's no time. As you see, I already ran out of time now. The Churchill province is different again. The Archean cratons like Superior and Slave, they are Neo-Archean cratons, okay, and they cratonized at that time at 2.5. And the Churchill province, part of it is a later belt, the Trans-Hudson belt, but much of it is also Archean terrain, but it got reworked again in the Proterozoic. So it got reworked in the Archean, in the Neo-Archean, and in the Proterozoic. And there are some kimberlites, but the younger ones, for instance, near Hudson's Bay, the younger ones don't have any diamonds, and there are a few older ones that have diamonds, but they are generally small. So there are some areas in the that are being explored now, for instance, in the region on the northern part of Hudson Bay, and they may eventually end up with diamonds.
Okay.
And Herb, John Brister here. So the $1 million question, I mean, are you in your models and differentiating, say, the Carvel history from your slave history? You know, where does Andy's model fit in with the Clippers, or do you think?
Well, the Clippers, I don't know whether the Clippers have anything to do with the Archean history. The Clippers come when the kimberlite gets intruded, right? And we think that the Clippers form just before, somewhere in Andy's nice model with that body cooling and all the fractures going out. That happens more or less plus minus 10 million years before the kimberlite eruption, or at the kimberlite eruption. It could be one part of the kimberlite eruption. I don't think that has much to do with what the craton looks like. On the other hand, the craton, the Kaplan craton, the type craton, is really the only major craton in the world where Paleoarchean blocks have come together at the end of the Mesoarchean, and the action stops. Everything else is platformal afterwards. There's the bushveld coming in. There are all these other events taking place, but the root down there stays still, right? There isn't all that much apart from the bushveld happening to it.
Hi, Bill McKechnie here. It was a very good talk. Thank you. It was very, very interesting. I was actually going to ask your opinion about the bushveld and its impact on the Carvel. It's quite interesting because the bushveld complex is virtually surrounded by diamondiferous kimberlites right close to the edge. And we have one diamondiferous kimberlite sitting right in the middle at Palmitgat. It's got very strange diamonds, 3 populations of diamonds, black, green, and pure white. I think very few people have seen those things, but it's very, very interesting kind of setup. You know, on the southwestern side, you've got Swartruggens, you've got Zhuaneng sitting there over in the east, Marsfontein sitting up in the north, and Cullinan, much older, you know, sitting on the southern edge of the Carvel, of the bushveld.
Okay. So basically, today is just going to be a bit of a look on kimberlites, lamproites, and then the impact of some of the geological features on the sampling and the resource aspect of these bodies. Just in very brief sort of overview quickly, on the kimberlite side, just the key features of this rock type, some of the family and the varieties that you can find in kimberlites, shapes, pipe zones, textures, and then of course, how are they in place and how do you classify them? A quick detour into the lamproites, a little bit less detailed, but just some of the key features that you know are typical of lamproites. And then of course, I mean, kimberlites are volcanoes after all, so you need to understand a little bit about the volcanic processes to make sense of what's happening in the pipe and in the crater. Then just a very quick little bit on resource sampling, mainly for the young geologists that are attending. And then how do you pull it all together in terms of the geology, the geostats, and other properties that can actually assist you in compiling and constructing a fairly robust resource model. So in terms of basics, a kimberlite really is a fairly volatile rich, so CO2 rich, potassic, and an ultra basic rock, and it is characterized by a pretty low viscosity in general. So low silica obviously equals low viscosity. Being ultramafic, it's highly prone to alteration. And of course, as a result, partly of that, extra crater deposits such as lavas, etc., are rare. They do exist. We'll look at some examples, but they're generally rare. Because there are no current kimberlites erupting and haven't been for some time, there are no new examples to go on. We're completely dependent on looking at modern analogs in terms of volcanism to understand how kimberlites actually form in terms of the eruptive processes. They are the deepest known melts, so pretty special in that sense. And also because of that, difficult to reproduce experimentally. You'll appreciate that something that comes from 150 kilometers down will show quite a bit of modification before it actually eventually reaches the surface. And that is also quite problematic in terms of reproducing these magmas in a laboratory setting. They are part of a large group of related rocks, which we'll look at in a minute. And the majority of those are actually non-diamondiferous, which makes it a bit difficult. So you find them quite often during prospecting, but the really diamondiferous ones are not that common. And of course, to distinguish the kimberlites from some of the other rock types that are closely related to it, you need chemistry and some petrographic work sometimes to do that. This is a fairly old diagram, but I still, like it. It was published by Scott Smith in '95. And basically what you're seeing here is a group of curves. The height of the curve is basically proportional to the frequency with which these rock types are encountered in prospecting. So right in the center there in red, you've got your group 1 kimberlites. Next to it, the group 2s, then the lamproites. And then on either side, left and right, you've got a sac name known as melnoites. So that would include things like alnoites, melilitites, polsonites, etc. So they are basically going more towards your ultramorphic lamprophile suite. And then on the other side, the monettes, calc-alkaline lamprophiles, and similarly moving away from the kimberlites. And of course, the depth of melt separation then gets shallower. And then you'll notice that in the middle, these curves sort of overlap over here. And basically that is due to the sharing of some of the properties of the rocks. You get things known as K1Ms, which have some overlap in terms of properties between melnoites and kimberlites. The same, you get phlogopite-rich group 1s, and then the same happens between group 2s and lamproites, etc. In terms of kimberlites, there are really the two main types, group 1, and they are characterized by fairly depleted, isotope geochemistry, and then the group 2s, which are your micaceous kimberlites, and they've variably been known as micaceous, orangites, and lately, after some work by Pearson et al. In 2019, have been termed carbonate-rich olivine lamproites. Some examples of these types of kimberlites, the group 2s, that is, would be things like Finch, Voorspoed, Lace, Swartruggens, and then Roberts Victor. Those are just some of the common ones, or the better known ones in South Africa. As I've mentioned, isotopically distinct and phlogopite dominant in the case of the group 2s. The isotope signature definitely very much more enriched. If you look on these diagrams over here, you'll see these sort of rocks trending away. So the lamproites in sort of the light blue, and then the orangites or the group 2s in orange color there. So enriched signatures to the bottom and to the bottom right in terms of isotope space. So geochemically, higher potassium titanium, light rare earth enriched, and higher in barium typically compared to the K1s. And then, of course, there are some very close mineralogical, compositional, and as I mentioned, isotope similarities to the lamproites. They're also higher in CO2 and calcite compared to the lamproites, and hence the name that Pearson et al. Suggested for them, which, by the way, was, I think, proposed originally by Barry Dawson in the 80s already, that these rocks are actually closer allied to lamproites than the kimberlites. So if we look at the kimberlite shapes, just simply looking in the Southern African region, it's evident that there is a vast array of different kimberlite shapes and forms. And it's quite clear when you look at these different morphologies that the emplacement process is actually quite diverse. There are a number of factors which impact the shape of a kimberlite pipe, not least of which, of course, is the country rock geology, but also things like the magma rheology, the water content or availability of water, volume of magma, etc. So in this diagram, you can see basically your typical Arapa style pipe on the right-hand side, more of a Zhuaneng type with coherent or pyroclastic kimberlite in the central part of the pipe, with or without crater basins. And then you have your coherent only kimberlite craters, and then on the right-hand side, volcaniclastic only, and sometimes even just very small vents, and then things like blind domes and so forth. So if we go to the root zones now, so starting in the kimberlite pipe from the bottom upwards, on the left-hand side, you'll see some sections and plan views from the Wesselton pipe in Kimberley, and on the right-hand side from De Beers pipe. You'll notice immediately the very irregular shapes of these plan views. That is because the kimberlite at these levels basically have to use joints and fractures to propagate its way upwards, and therefore it does not represent such a smooth morphology as in the upper zones of the pipe. You can see here, for example, the W7 at Wesselton, a blind dome, it emplaced and it didn't get any further than, as you can see here, about 600 level on the maps. If we have a look at the rocks from this region, basically very dark. This is typically an uncontaminated sort of kimberlite on the top left-hand image, aphanitic on the left-hand side of the sample, macrocrystic kimberlite, and of course macrocrystic basically just being a non-genetic term referring to these anhedral large olivine insets, typically 0.5 to 5 millimeters in size. They usually refer to olivine, but they can refer to any mantle mineral, garnets, clinopyroxenes, orthopyroxenes, and of course even diamond, which of course if it's crystallized in the mantle, it's xenocryst in the kimberlite. Top right, thin section view. Of course, olivine crystallizes as a primary phase in kimberlite magma. So you see there the phenocrysts. And for comparison, in terms of size, there's a macrocryst on the left-hand side with the very fine-grained ground mass. Bottom right-hand side, also some examples of macrocrystic kimberlite. If you look carefully, dike within a dike, you can see there's the contact defining a dike in the middle, which is characterized by coarser olivine macrocrysts, finer on the edges over here. And then an example of a hypabyssal kimberlite, and this shows one of the other typical features of hypabyssal or magmatic kimberlite, and that is the thermally altered country rock fragments that you see in these type of rocks. These are all basement gneisses that you can see here, these white sort of blobs. They've been quite heavily altered. Up at the top left here is a shale or a mudstone, which also shows a thermal alteration pattern on it. Moving now to the diatreme zone, and for that we move up to the north of South Africa on the border with Zimbabwe. The Venetia pipe or cluster, essentially four main pipes and a whole lot of smaller plugs and dikes, all of which give or take 500 million years old. They are intruded obviously in the central zone of the Limpopo mobile belt, so very high-grade metamorphics for the wall rock that it intruded into. And these rocks basically range from purely magmatic through to pyroclastic and also some reworked volcaniclastic material. But basically the reason for this particular example is to show you the diatreme zone facies, or the rocks which are found in them. And these are some examples of very, very typical diatreme facies kimberlite. So this occupies the sort of the central zone of the carrot, if you like. You'll notice the rock is very well mixed. It's pretty homogeneous looking. And you'll also see that the country rock fragments that you can see in here are actually fairly pristine. They are not very thermally altered. There's one example here, which is a little bit of a halo. And also on the photograph on the right-hand side, you'll see that all of these fragments are still fairly fresh. In terms of the mesostasis or the ground mass, a primary pyroclastic rock typically contains between 20 and 30% porosity. So all of that space has been infilled here with hydrothermal products, things like serpentine, saponite or magnesium-rich clays, chlorite, brucite, etc. These are the dominant minerals that have been analyzed from this ground mass. You'll notice also that it is actually quite difficult to detect pyroclasts in this rock. You don't really see them. The reason for that is largely because they are very thin rim, usually in the diatreme zone. So they are extremely difficult to spot. Under thin section, of course, under a microscope, it's a different story. You'll see them very clearly, but in hand specimen, they are quite difficult to identify. But every now and again, you'll find some rocks where you see some really spectacular features, and it leaves you in no doubt that the rock is actually volcanic and more specifically pyroclastic. You can see here the very, very prominent pyroclasts. These are all altered basement clasts or basement clasts. They're not that altered. You can still see amphibole and biotite in that one. And then the brownish sort of rim from the pyroclast around it. So unfortunately, very seldom this spectacular, usually quite a struggle to see those pyroclasts. And then if we move up onto the crater, this is the geologically most complex part of the actual kimberlite, and in fact for many volcanoes, for the simple reason that you have in this area of the pipe, you have a combination of both primary pyroclastic as well as volcanosedimentary deposits. And all of these actually behave differently with respect to diamonds, and indeed the processes that form them are actually quite divergent. So what you're looking at here, the top left, this is the Orapa kimberlite pipe in north central Botswana. Dual pipe or double pipe system. There you can see the north pipe over there, southern larger pipe to the south, and you'll notice that the south postdates the north. It has truncated the top of the north pipe. And in here in the south, a complex array of volcanosedimentary as well as pyroclastic sequences overlaying the more straightforward sort of pyroclastic successions at the bottom. And then just for comparison, over on the top right-hand side, there is an olivine malilitite crater. This particular one is Lolmurwak, which is in the Lake Natron Ingaruka monogenetic volcanic field in the north central part of Tanzania. And for comparison, there is a scoria cone, so Mar crater on top, scoria cone on the bottom, and you'll notice the sort of lopsided view of this scoria cone. It's because the wind was blowing from right to left at the time of eruption, and it deposited the bulk of the ejecta on the one side of the pipe, very little on the right-hand side, most of it on the left. So the complexities not only inside the crater, but also in the extra crater tuffering material, depending on weather conditions, volume of magma, violence of the eruption, and direction of the blast, you can have very, very different looking craters in close proximity to each other. Another example of the variability that is evident in a crater, this particular sequence of photographs were taken between June 2007 and June 2008, and is from the Aldonialengai carbonatite, or the crater thereof. And you'll notice that you go from a crater that is almost totally filled and showing various little hornitos and individual little vents inside it, to, after a fairly catastrophic eruption, a huge hole in the top of the mountain, and everything blown out, and basically a totally different environment. So this is within the space of only 12 months. And things can be very, very fluid in a crater environment. And of course, bear in mind that what you eventually observe when you drill your kimberlite is the last phase of eruption, or the last sequence of activity that took place. And you basically have to decipher what happened prior to that. This particular example is a pipe in East Java. This is Raung stratovolcano as it looked in 2015. The reason for this photo is just to illustrate that you get a complete transition in many volcanoes, and kimberlites are no exception. Here you had a very violent caldera eruption. The crater is 2 kilometers across. That was followed by a period of quiescence, and basically the floor of the crater filled up with a lava lake, as you can see over here. And then it resumed explosive activity. slightly less violent. There's a double scoria cone in the background there, and the rear vent is active, the front one dormant. So this combination of quiescence and explosive activity is something that you also see in kimberlites. Dominantly explosive in the case of kimberlites, but lava lakes do occur, and we'll look at some examples in a bit. So moving on to the emplacement and the classification of kimberlites. There are both mineralogical and textual classification systems in use or available and have been published and written about. The mineralogical classification dates back to the late 70s, Skinner and Clement, and was largely based on the main groundmass minerals. But the primary nature thereof was quite a contentious issue. Initially in that paper, minerals such as serpentine and calcite were deemed to be primary. Experimental work has since shown that minerals such as serpentine can't be stable above much beyond 300 degrees, which would effectively make it a hydrothermal type mineral. But nonetheless, minerals such as monticelite, phlogopite, etc., those are very much primary. In terms of the textual classification systems, there's a whole plethora of papers and work done since the late 70s all the way up to very recent. Right, there we are. So basically, we said that there's ongoing debate around the kimberlite emplacement, and as a result of that uncertainty, there's a lot of different and diverging opinions on some of these classification techniques. There are basically two main emplacement models, the magmatic versus the phreatomagmatic, and we'll have a look at each of them individually quickly, just to set the scene. However, before we get there, essentially kimberlites are really volcanoes. So one of the preferences that I have is simply to stick to a volcanic and a volcanosedimentary system, which is commonly known and is understood by scientists the world over in terms of these when you classify or when you describe your rocks. And so these are basically the systems that we're currently using in De Beers on the operations to actually log and to map the kimberlites. So in terms of the magmatic model, it's basically pertains to a sudden release of a magmatic vapor and gas system. So in other words, it's gas driven, and it usually relates to a decompression effect close to surface and as the magma ascends through the subcontinental lithosphere. There's basically the eruption is dry. There's no interaction with groundwater, unlike with the phreatomagmatic model. Dawson introduced the concept of fluidization, which did not remain entirely consistent over the years. The definition of what fluidization actually involves did change somewhat over the years. For example, in the case of Clement, who advanced the model further with the concepts of the embryonic pipe formation, fluidization basically refers to the upward, or sorry, the downward movement of a degassing front into the pipe, whereas Sparks basically views fluidization as the upward flow of gas through the pile of the ejector. And the most recent work on this, on the magmatic front, basically was the 4-stage model by Sparks in 2006. On the right-hand side, starting with the stage 1, you have a narrow conduit, typically a fissure or a small pipe. When the eruption commences, of course, there's an overpressure situation. Material is ejected from the system, and the eruption continues. But with time, obviously, particularly the upper parts of the crater become unstable. It becomes broken. It collapses inwards, and of course, in doing so, the vent widens and the pressure then decreases. Once this process carries on even further, at the point where the pressure of the eruption is equivalent to that of the atmosphere, internal deposition now becomes possible in the vent. Fluidization processes may be active as well. And usually from that point onwards, particularly large, coarse blocks, etc., big particles are no longer able to be ejected from the vent, and the vent may in fact become choked off at the bottom, depending on the stability of the wall rocks, etc. And then, of course, the last phase of this particular model is then the hydrothermal alteration, which then pervasively, flows through the pile of ejecta from the source of heat at the bottom. And then, of course, this model of emplacement is unlikely to be a once-off bang. It usually, with any volcanic system, or the period of activity is usually measured in at the very least weeks and mostly months and years. Moving on to the phreatomagmatic model, this is a very common process across many magma types, not just kimberlite, but it extends all the way through to andesites, dacites, and is a very, very commonly seen emplacement mechanism in volcanism. And it basically involves the ascent of magma and then interacting with groundwater, either in fractures or in aquifers, etc. In doing so, it usually produces fairly violent explosivity, as you can imagine, when a hot magma comes into contact with cold water. The diagram on the bottom left-hand side basically gives you an indication of how this works. So there you've had your column of magma rising, you intersect the groundwater, and you generate an explosion. And then one of two things can happen. You can either use up the groundwater, in which case the scenario is very similar to a well being overdrawn. And of course, as the cone of depression develops in terms of the water table, the point of explosion moves further and further downwards, and thereby deepening the crater. I should also add that the explosion or this explosivity only happens very close to surface. Anywhere below 300 meters, usually you cannot produce an explosion due to the high confining pressure. So this is very much a process happening near the Earth's surface. If water supply is abundant and exceeds the rate of supply of magma, then all you do basically is generate a bigger and bigger crater in the ground, but remaining more or less at the same elevation. So you generate something that looks a bit like a champagne glass or a soup bowl, rather than a steep-sided vent system. And of course, with all the water around, you can imagine that the alteration of the volcanic ejecta is going to be quite substantial over short periods of time. One of the recent or last advances over the last couple of years have been the fact that there's been observations in some of the work and vent systems that have been studied, that once the diatreme has been established, depending on the level of water, and for example, if there's significant amounts of rain, water may percolate down and you may end up having magma ascend to higher levels in the pipe again. And this process basically leads to the formation of tephra or debris jets. Of course, if this process reaches the surface, you'll generate another little vent inside the bigger original diatreme. If not, then what you will do basically is just develop a region of highly disturbed and disrupted volcanic products down in the actual vent itself. Some of these features have been observed in kimberlite, and there's potential examples of it here. This particular photo on the left was taken in Arapa in the North Pipe. And there you can see the contact of one of these vents running down on the left-hand side is the one edge, and the other contact on the right-hand side over here with a adult for scale in front. You can see it's quite a few meters across. Very poorly sorted. You can see the large boulders inside of it. And then the photograph on the right-hand side, this particular example was taken in the early days at Lefakane, circa 1984. And you can see the little funnel-like structure here extending over about 3 different benches. So for scale, a bench is about 12 meters here, give or take. So you can see more or less the size of these little vents. And on the left-hand side, just the same picture that you saw just now, but I zoom in on the actual contact position. You can see the host over on the left-hand side, poorly sorted. There's the contact running just to the right of these wet areas, and then the material to the right, a lot finer grained. You'll notice down here some slump and joint structures also evident here. Then in terms of some real examples, one always sees these perfectly drawn cartoons in papers on what diatremes and vents look like. But if we go to the south of Japan, there's a little island in the Philippine Sea where there's a volcano known as Miyakijima. Now, in 2000, this volcano erupted catastrophically and blew a large caldera in the island. But prior to that, there was a series of phreatomagmatic maars that actually occupied the island. And this caldera basically truncated one of these maars in a perfect section view. And this is what you can see over here on the right-hand side. So on the top there, you can see the lake, the old crater lake, the crater lake deposits just below it, the central sort of vent area, highly disrupted, poorly or unbedded material, in fact. And then on the edges here, more sort of gradually dipping angle of repose, sort of sorted and layered and bedded units. Down here at the bottom, you can see an example of a slumped piece of the wall rock, the so-called floating reefs in kimberlite. You can see the offset there on this white unit. And note the small size of the feeder zone, the feeder dike down here, and there the actual vent starts. So a really, really spectacular example of a real diatreme. So a lamproite is really a per-alkaline, ultrapotassic, and perpotassic rock. The definition of a lamproite, the one important thing is that it cannot be done based on the modal mineralogy only. Textures are quite important, and compositions in particular are fairly essential. Because of the large number of liquidus phases and because these are small degree partial melts, there's considerable mineralogical diversity in these rocks, and also in the greater sort of lamprophile suite outside of lamproites and kimberlites. It's important to note also that lucite is not an essential mineral in lamproite definition, but it is most definitely characterizing. So in terms of definition or classification rather, the work by Scott Smith and Skinner in the 80s basically provided a very good system for subdividing these rocks. So you can start from a olivine rare lucite rich variety, moving all the way across into an olivine abundant lucite poor or absent rock. And of course, there are some very key characteristics associated with these mineralogical changes. First of all, your diamoniferous varieties are only found in group 3s, where these are your deeper magmas in terms of within the lamproite group itself. And then the other thing is the morphological presentation of these lamproites. Your group 1s, being more silicious, tend to be preserved as positive relief features, whereas your group 3s, being more mafic and more prone to weathering, generally tends to be weather as negative features. And if you look at the mineralogy very quickly, on the left-hand side, these are the typical minerals that you find in a group 1 and to a degree group 2, with the exception of monticellite ground mass. On the right-hand side, these are the minerals that you see in a lamproite. You'll notice there are some that also occur in both the perovskite, the apatite, etc. But note that the compositions are actually quite distinct. The apatite in the lamproite is very fluorine-rich, strontium, barium. Same for perovskite. The amphiboles are very titanium-rich. The phlogopite compositions are also different. So although the minerals are showing the same compositionally, they're very much different. In lamproites, thus far, it definitely is the case that your pyroclastic or your volcanic plastic deposits do carry higher diamond grades than the magmatic lamproite varieties. And then the last couple of points, very important to note that if there are more sodic minerals present in the rock, then it is unlikely to be a lamproite. So things like plagioclase disqualify it. Minerals such as melalite, monticellite, calcillite, nepheline, any of these feldspathoids, etc., would disqualify the rock from being a lamproite. And then things like these iron and titanium-rich garnets, also diagnostic of other rock types rather than lamproites. In terms of the morphology, top left-hand side, this is basically Ellendale, and you can see Ellendale 6. This is a group 3 lamproite. These ridges, by the way, are the country rock geology. This is not the lamproite. The lamproite is sitting in between here. You'll notice it's completely flat. There's no topographic expression. Contrast that to a lucite lamproite, Mount Weld on the right-hand side, and you'll see a nice little hill with the magmatic lamproite sitting in the middle as a sort of a lava lake. And then lastly, just bottom left to note, this is Argyle. As with kimberlite, you can most definitely also find multi-vent complexes, the same as kimberlites. These are also volcanoes, so in terms of the volcanological characteristics, there's no reason that they won't also show some of these features. Moving on to some volcanic processes. As we said earlier, there are no current volcanic eruptions going that would represent a kimberlite. So therefore, we have to look at analogs in modern volcanism to understand how a kimberlite would have been placed. The historic emplacement models for kimberlite are largely based on or have focused on end-member volcanic processes. So in other words, for example, a gaseous eruption would, for example, rather be focused around airfall and maybe some pyroclastic flow type processes. The phreatomagmatic model, on the other hand, would encompass processes such as pyroclastic surge, also with a bit of airfall. But it's worth remembering that in volcanoes generally, there are 3 key processes that always occur regardless of magma composition, and that would be the airfall, your pyroclastic surge, and your pyroclastic flow. The other point to note is that these never occur in isolation, or very, very seldom. They are always mixed. For example, airfall will always occur with surge and with flow. So these processes cannot be divorced from each other. They do occur together. And I think that has led to a lot of the initial debate and arguments regarding the emplacement of kimberlites as well. So let's just have a look at kimberlitic lavas. We mentioned early on that they are very rare, but if we go to the central western part of Tanzania, northwestern part of Tanzania, there's a kimberlite known as Igwizi Hills, a very young kimberlite, by the way, less than about 12,000 years old. A triple vent complex, Mar crater on the top right-hand side, and then 2 scoria cones. But what is significant about this particular occurrence, apart from its age, its very young age, is that there were copious kimberlitic lavas produced here. The Mar vent actually overflowed and produced a lava flow to the northeast. And similarly, there were lava lakes in the 2 tephra cones or scoria cones to the southwest. So the system youngs in age from northeast to southwest. And this is one of the best preserved examples of kimberlitic lava flow. And here on the right-hand side, you can see a section through this lava flow. You can see the very vesicular top of the flow over here. And then moving downwards, you'll see it becoming progressively enriched in olivines. That's these black looking shapes over here. And in thin section there, you can see the olivines. And then the vesicles, the more irregular vesicles up at the top of the flow. And then just for comparison, over on the left-hand side, this is a carbonatitic lava from Aldonia Lengai. It literally flows like water, and you tend to form these very, very thin little almost pancake layers of these lavas. So if you alter this, take it for a few million years, alter it, you'd be forgiven for thinking that it might be quite well bedded pyroclastics. Another example over here, if you have a little sample here in isolation, looks very lava-like, maybe even segregationary hyperbissal. But this points to the hazards of actually looking at a sample out of context, because when you look at the full sample, you will actually see that it is a pile of compacted and sintered pyroclasts in a volcanic package. So what you were looking at initially was the bottom part of this unit. As you move upwards, you can start seeing the individual pyroclasts with the ash in between it. So very, very important to always refer to the geology adjacent to a sample that you collect in order to get the full picture. So if we look at airfall processes, these are some of the very distinct features that you can see for an airfall deposit. First of all, on the top left-hand diagram, very well sorted in this particular case, quite clearly class supported, some thin surges in between as well. Your airfall deposits typically mantle the topography, they drape, and you can see a very homogeneous sort of layer of class supported pyroclastics over here in the top right-hand image. Depending on weather conditions, you can find very extreme sorting of airfall deposits. This is Krakatoa or Anak Krakatoa erupting, very strong wind blowing, and you'll notice the airfall deposits being deposited downwind from the vent. And of course, the sorting will take place as well. As you move further away, you'll be going smaller and smaller in grain size. Basically, moving on to the pyroclastic flows. So these are essentially very high density gas solid surface flows which run down the side of a mountain. They are gravity controlled, essentially very, very destructive and capable of carrying a considerable load of debris. This bottom right-hand example is a flow from St. Helens. You can see the amount of debris in this particular flow and also the neat contact where it actually stopped. That is typical of these sort of features. They usually form either from a column collapse or from a lava dome collapse, which of course is not relevant in kimberlites, but definitely from column collapse. And you do see these features in kimberlites. Here is an example. If you look at unit 2 on the left-hand side here, this is a pyroclastic flow deposit that was mapped in the south crater of Arapa. Fumarolic structures, high temperatures, and this was confirmed through some temperature and magnetic work that was done on these lithologies. It was definitely a hot event emplaced or surrounded by volcanosedimentary units above and below. So indication that the vent was still fairly active late-ish in its life. Pyroclastic surge, these features are basically a more gas-rich equivalent. They carry a lesser load in terms of denser material, but in doing so, they're also able to travel a lot further, also across water. The top of a pyroclastic flow can detach and form a surge which may head off entirely in its own direction, depending on the topography. These typically form either as lateral blasts from a vent in phreatomagmatic conditions. As you can see over here, a little valley coming down from the crater filled with these pyroclastic surge deposits. And accretionary lapilli, as you can see in the bottom left-hand side, which are essentially pyroclasts coated by ash. These are totally diagnostic of these pyroclastic surge deposits. Usually because of the presence of steam and electrostatic charges, you get ash wrapping around the rims of these pyroclasts. They're very delicate though, and they get easily destroyed. We see these in kimberlites as well. Bottom left is an example of a surge in Voorspoed. This is an example of some low angle crossbeds in surges from Zhuaneng. And here is another rotated block from the Tuffering, which fell into the crater. You can see the very prominent bedded units in there. Some thoughts on resource sampling. The one thing, of course, is that confidence in a resource does not come cheap. And also there is, particularly for the new geologists or the guys who are now thinking of starting a career in geology, there's no thinking out the box when it comes to sampling. There's no quick and easy or thumbsuck or any shortcut to the sampling process. You unfortunately, if you want to do the job properly, you need the data, and therefore the sampling has to be done. It's expensive, of course, and so nobody likes to do it, least of all the accountants. The other point to note is that when you consider sampling, the variogram of that particular deposit, which I'll talk about in a second, should govern your sampling. So you actually need to take some samples so you can construct a variogram before you even start your main sampling campaign. So in terms of estimation, a valid estimate for individual blocks can only be obtained when your variogram range exceeds the resource block size that you pick and your sample spacing by a generous margin on a defined drilling grid. Another thing that people love to do is to actually use delineation holes for resource definition. Preferably, it should be done on a previously optimized drill grid. Leave the delineation holes for the geology work. And the unfortunate thing about sampling is that if your sampling campaign is inferior, you will not realize it, because you will still get grade estimates and you'll still be able to populate your blocks. However, unfortunately, the confidence on those numbers will be very much less than what you were hoping for, even in the type 1 or the long-term block models. So if we just briefly look at a sampling campaign, just some theoretical holes in blue over here, the relationship, the statistical relationship and spatial relationship between these samples are defined by what is known as a variogram, and that is simply a relation of the variance over distance between the samples. So these points over here are basically the sample pairs that you're plotting as a function of distance. And one of the very important features of a variogram is this point here, the so-called range, because at this point, you move from correlated statistics into uncorrelated or random statistics. And that has a very, very big impact on sampling and the reliability of your samples. So let's, for argument's sake, let's say you decide to remove some samples from your carefully optimized grid. You can see that by removing the yellow samples and also the orange samples, if you were to remove these holes, you would remove much of your correlated statistics in your drill grid. And you would essentially be having a spacing that is uncorrelated. So in other words, the red samples don't talk to the blue samples at all. And that has a very big impact in terms of confidence for a block estimate. And not only do you lose that correlated statistics between the holes, but you also then, of course, lose the information of the holes themselves that you've taken out. So there's a double whammy. It's the holes that you've removed, but you've also degraded your entire sampling campaign. So this is definitely worth keeping in mind for those going into economic geology. So then on to the last section, just pulling the whole lot together. What is possible in terms of the various techniques. In terms of resource risk, what is the degree of the internal geological variation that you're dealing with? Is your deposit looking like the example on the left? Is that the geology that you're seeing? Is it very complicated over small distances? Or is it like the example on the right? Is it fairly monotonous and massive? And then, of course, what causes this variability? Is it volcanosedimentary processes? Are they pyroclastic processes? And how could this impact your diamond grade? It's important to identify the major geological units which impact your diamond grade and revenue. It's easy to get carried away looking at all the textural and visual differences in these volcanic rocks, which are very abundant and very common because, I mean, the crater is a very heterogeneous and very violent system, and it produces a lot of textural heterogeneity. But it is important to focus on the actual differences that impact your grade and your financial parameters in the resource model. And one of the best ways to do that would be to look at chemistry. These are just some examples of ground mass spinel plots, pulling apart various magma signatures in different pipes. This is Koffiefontein, Voorspoed down at the bottom. That was a Victor in Canada that we heard about earlier. And so through some careful analytical work, one can go some way in supporting the modeling decisions made. Most of your geological parameters are also regionalized variables, things like dilution, rock density, rock strength, dense media separation yield, etc. So once you can show that a variable is regionalized and there's a spatial structure to it, you can then, of course, also estimate it through processes like kriging, or you can simulate it through conditional simulations. And that allows you to move to a different level in terms of risk definition. You can then create block models from these parameters, and that could be an additional input into your mine planning process in terms of either treatability, rock strength, or whatever the case might be. You can also generate from this, of course, probabilistic models. Here is an example of the probability of your UCS, your rock strength exceeding 40 MPa per individual block. Down at the bottom there is DMS yield, another block estimate of a metallurgical parameter. Then, of course, probabilistic methods can also be used to simulate your actual pipe volume, and then also plan your drilling according to a maximum reduction on variance that you can get from these sorts of exercises. Similar type of techniques, so stochastic uncertainty principles, etc., can be applied to your diamond size distributions and valuations. There's been some work done on that and published that you can go and have a look at. And then in conclusion, so as you've seen, both kimberlites and lamproites are part of a complex and quite variable group of rocks, very few of which are diamondiferous, and therein lies the rub, and the ability to recognize what is a true kimberlite as opposed to a malnoite or some parakimberlitic variety is quite important. As you would have seen and hopefully realized from this presentation, your kimberlites are essentially governed by the same processes as in any other volcano. They are volcanoes themselves. The magma composition is very, very unique, but the actual volcanic processes are no different to any other volcano. And so, of course, keep an open mind, because no two vent systems are ever exactly identical. They do have their own personality, each one of them. It's important to corroborate your visual geology with analytical techniques. Your textural and your visual features do not tell the full story, and in fact sometimes overcomplicate your geology, as for reasons I've just mentioned. The textures, one tends to be naturally drawn to the visually different in the geology, but that does not always correlate with what is economically sensible. The geological units that you do define must be accurately portrayed in terms of key resource parameters. So principal of those would be diamond grade, diamond revenue, dilution, and your ore treatability. Those four would be the paramount characterizing features that you should try and build into your resource model. And then, of course, a range of uncertainty is always better than a single value in terms of confidence and quantification of risk. And then, particularly for those of you, the young guys interested in going into economic geology, try and be proactive in your use of geology. Try and alert the operation or the mine to future ore treatment problems, grade changes, etc., rather than explaining it after the event. A very common theme that something happens and then one has to try and explain it afterwards. Whereas with a little bit of work and foresight, you could have alerted operations to it. And then after your geological definition, just to close off with, of course, your next most important thing is an appropriately optimized sampling campaign. That is probably the single biggest area of downfall where prospects and projects have failed in the past. And that, I think, brings me to the end, other than to just alert you to a new paper coming out soon authored by Mike and myself and a couple of other people. Look out for it. It should be available pretty soon. Thank you. Apologies for the delays halfway through.
That was a very comprehensive talk, and particularly for people who may be just entering into the world of diamonds and kimberlites. It's worth reviewing this every once in a while. The geological complexity is significant in many kimberlites in many provinces. There's probably time for one comment or question. If anybody would like to raise their hand or just unmute themselves. There's a couple questions in the chat box. Is it possible to determine the rate of emplacement per kimberlite facies?
Yeah, I'd have to think about that a little bit. Look, I mean, the rate of emplacement depends to a large degree on the volume of magma available. And then, of course, the difficulty in which the magma has to find a path to the surface. Generally speaking, volcanoes or the magmas do ascend very, very quickly. I mean, if they didn't, then there wouldn't be much left of the diamonds, because they do suffer quite a bit in the actual kimberlite magma. So the ascent is pretty rapid. In terms of the actual volcanic emplacement, once you get to surface, that would be entirely, or not entirely, but significantly controlled by the conditions encountered close to surface. So in other words, is there water? Is it high-grade metamorphic rock, or is it soft mudstone that it has to emplace into? Yeah, and then I see there's another part of that question. Does olivine abundance have any relation to diamonds? Yes and no. The amount of juvenile material in the kimberlite does have a rough correlation with prospectivity, if we can call it that. But remember that olivine doesn't only occur inside of the diamond stability field. At shallower levels in your graphite stability field, you also have olivine-bearing rocks. And these olivines would be added to the load as the kimberlite passes through. So to take a count of your olivine and to try and equate that to a grade is a little bit hazardous, because there are barren areas, of course, that you will be passing through, where you will be sampling olivine, but which may carry no diamonds. So yeah, it's not as straightforward as you know, a simple correlation between the olivine, but obviously the more diluted the rock is with country rock fragments, the lower the grade potentially could be. And of course, I mean, olivine in itself is also a dilutant. Of course, for every olivine crystal, you know, you take space away where you could have had a diamond.
Yeah, it's an interesting one though, Johan. I mean, you were aware that generally, you know, when we looked at kimberlites, if you saw lots of good macrocrystallic stuff and plenty of you know, good garnets, you always got excited about them. And I think there's that story, and I think it was at Letseng, where in the early days, you know, if they wanted to get to the better grade or high grade kimberlite, they'd give guys a tin and go and count garnets across the pipe.
Yeah, no, look, there is that, John, you're quite right. Really speaking, the more juvenile material you have,
yeah,
you know, the better chances are. But it's not as, I know that there's been some work done in the past looking at olivine sizes, even, you know, as a correlation between olivine size distribution and diamond size distribution. But it's very tenuous. It may work in some instances, but it depends also which facies you're looking at, etc. It's not a technique, you know, in all honesty. I would far rather sample for the actual diamonds than to try and to decipher the olivines. You know, once you've done the correlations, you've taken the diamond samples and you've counted the olivines in them, you could maybe make some pronunciations on that, but I think not without any diamond samples.
By way of introduction, I was invited to go to Angola by the Mines Ministry to give this talk in its original version, which was on the 25th of November last year. That was on the first Angola International Diamond Conference. It was a heralding of a new era for diamonds in Angola. And it was a privilege to be there and see the development since I was last in the field in Angola, which was around 2006, 2007. So I actually used the opportunity to go into the field just when Omicron hit South Africa. And it was a very useful visit at that time to renew myself with the terrain. This front piece here has a diagram on the right-hand side, which is attributed to Maggie Loubser. It was commissioned by De Beers. And it shows crater facies kimberlite, both erupting, the huge volcaniclastic cloud, and preserved with lenses of crater facies material in here. It turns out that environment is very well preserved in the Angolan setting, And so this diagram on the right-hand side is a very useful sort of prompt to what I will be talking about during this talk. The title of the talk is The Geology of Angolan Kimberlites, and there's sort of an add-on at the end, and diamond quality compared to regional production. This is actually the topic they wanted me to cover during the conference, and I do cover it in 3 slides right at the beginning by talking about diamond quality, and in particular dollar per carat values. And as you can see in the picture on the left-hand side bottom, diamonds vary in quality and therefore also in price point. I'll show this this diagram on the left-hand side here, which is diamond prices in US dollar per carat for the past 4 years. This is a lot of data that I've compiled from various different sources. And notice there are 4 different colors on this graph, which is a log scale graph. It's a log 2 scale graph because diamond prices do vary over a huge range from very low to quite high. The colors in gray are Kimberlite process certificate numbers. Those are publicly available. In green, they are from a primary kimberlite pipe. In blue, obviously, is an alluvial production. And we'll see a bit more data in orange. These are for the type 2 diamonds, of which Ray Ferraris gave us a good talk yesterday. And so on the first diagram on the left, we have all 4 colors represented. And starting at the bottom there, you can see that the price point for diamonds from Katoka in bold green is similar to the global price for diamonds, the KPC diamond number. There is a higher quality in 2 other pipes. I just want to get my pointer going here. These are them over here in green. This one over here is Kamutwe. It's a low-grade producer, but it's got very nice diamonds in the north of Angola. This one here is Kamachia, formerly known as Luo. It's got a slightly lower price point. More recent data has pushed this price point up, but it's useful to know that the alluvial diamond price point that you see in Angola is covered by producers that have similar quality diamonds, at least in terms of price. Then talking about the alluvials, there are 2 major alluvial producers. You can see them here, their price points. I'm not going to give their names. And then there are other minor alluvial producers in Angola, and all of their price points are in this sort of bracket over here, the alluvial bracket, which is similar to at least 2 primary sources that we know about. If you look at the integrated price for KPC Angola, which is this over here, then it's a blend of, it's weighted roughly 80% Katoka plus 20% alluvials to get you into this price bracket over here, just above $130 a carat. And then in orange, right at the top of the graph, we'll speak a bit about that project as this talk evolves. There are type 2 diamonds at Lulo. They fetch really high prices. And so they've attracted a lot of attention. It's a prime product that's now coming out of Angola. If we now compare the prices that we have for Angola production on the left with the SADC region, that's the Southern African region. I've got select dollar per carat values over here. And then let's start with the big guys. We don't have any dollar per carat prices for De Beers mines in the region. De Beers does not publish those numbers. They never have. But if you look at the Kimberlite process certificate for South Africa and Botswana, that obviously reflects these major producers that are in the De Beers stable, Jwaneng, Araba, also Felicia. And you can see that there's the KPC for Botswana. That's the integrated price point for Jwaneng plus Araba combined, plus a little bit of Karowe. Here's the integrated price point for South Africa production. That's mostly Venetia, but then also a number of other producers. And these two price points over here are exactly similar or broadly similar to what you get out of Angola. So in terms of the average diamond quality that we're getting out of the Southern Africa region, it's in this region over here, and it has been like that for the past 4 years, at least the years that are now represented in KPC numbers. Kimberley and Finch together are operated by Petra. There they are over there. Primary producers. The numbers have dropped off over the past couple of years, in particular at Kimberley, but also at Finch, in terms of the price point that they're getting for their diamonds. But the price point they've been getting out of Kimberley and Finch has been very similar to what they're getting out of Kotoka over these years. And I don't think a lot of people realize that this is the actual situation with diamond prices for these two primary producers in Southern Africa. There is a big difference though. Kotoka is an open pit operation. Kimberley and Finch are long life underground operation. And so the profit margin on that price point, the revenue that you're getting from your diamonds, is actually quite different for these two producers. We can think of Kimberley and Finch becoming marginal operations. That's definitely the case. Petra has recently disposed of Kimberley for that very reason. But Kimberley is holding its own under private ownership, and that's a good thing for South Africa. Moving on to alluvials, you can see we don't have very good data for alluvials in Southern Africa. It's a very fragmented industry. I managed to get some data from Transhex, which has now been delisted. Their Barken product was very high quality. Their Richtersveld product was also decent quality. Shallow water, that was from some Namibian operations, was mid in the price point over here, and then the West Coast operations were slightly lower in price point. But we have to remember that Namibia's KPC price point is basically all alluvial diamonds. They are very far traveled, but it's a placer alluvial, and you can see that's at about $490 a carat, very consistent through these 4 years, which is in the same price point that you get for alluvials in Angola. So there's a different way of looking at the diagram on the right here, and that's by orange washing it. In other words, let's look at the distribution of diamonds price points, average price points for producers that produce type 2 diamonds in the SADC region. That's what this picture then looks like. Everything in orange on the right-hand side produces type 2 diamonds. So let's start at the bottom here. That's Cullinan. It's famous for some very, very nice type 2 diamonds, but the average price point for diamonds coming out of Cullinan is this price point that you see over here. Those are numbers from Petra's annual reports. And so the proportion of value in the total production from Cullinan that is attributable to type 2 diamonds is relatively small. Williamson in Tanzania, also previously known as Madui, is a well-known producer of type 2 diamonds, in particular bubblegum pinks. And we can see a slightly higher average price point for Williamson over these years that I were able to get data from. And then there's a range of Matai, Karowe, Koffiefontein. These are all producing type 2 diamonds in this range, roughly about $500 a carat on average for the production on an annual basis. The standout type 2 producer in Southern Africa is Letseng. And interestingly enough, the diamonds that they're producing from, let's say, it's their main money-making characteristic, is a similar range as what we get out of alluvials at Lulo. Interesting fact. So the question is, where is all the orange in the rest of the Angola profile that we see on the left here? We're expecting to see some orange in some of these sources over here. I think they have largely been unrecognized in Angola. There may well be, or in fact, there have to be primary sources in Angola that also produce type 2 diamonds, and which then end up in the alluvials. We just haven't found them yet. And we can do a little bit more diamond intrusion studies and research on the actual productions coming out of Angola to be able to elucidate the proportion of type 2 diamonds that are masquerading as other diamonds in this part of the diagram here. So I won't say anything more about diamond quality, but this is a very useful way of looking at diamond quality from Angola in comparison to the rest of the Southern African region. So let's move on to geology. The benchmark for geology of kimberlites in Angola is Katoka. And it's because it's been going for such a long time. They started it up in 1995. The numbers you see at the bottom there goes up to, in the table, goes up to 2020. If you go look in Katoka's annual reports, all these numbers are available, right down to the price points, the grades. And so we know that in this period, while this open pit was getting deeper, they've mined out 186 million tons of ore. And they've done so at roughly $65 a ton. And they've made good money. Their internal rate of return is about 15 to 20% at $65 a ton. But the interesting fact that a lot of people don't realize is in the same period, they've mined out 330 million tons of what they call sterile. 180 million cubic meters, 330 million tons of internal waste. This is crater-facies material that has come out of this open pit, and it's taken them 26 years to do so. So let's go look at that in cross-section. Here's the plan view that you've seen in Google Earth images in the previous slides. And you can go to an 11 IKC abstract by a guy called Vladimir Pervov and João Felix. João Felix is the chief geologist at Angola, at Katoka. And they've given us a very useful cross-section of Katoka. Let's look at the geology. Unit 1, which is this light blue material over here, is the primary volcaniclastic kimberlite. These are ore reserves. They lie in the future of Katoka. We'll see that in a moment. Units 3 and 4, which are these green and pink colors. It's a resedimented, it's a rim of resedimented volcaniclastic kimberlite. It's ore, 186 million tons of this stuff has been depleted. And it forms an annulus around the outside of this big open pit. Units 5, 6, and 7 are crater sediment. That's this stuff in light brown and the stuff in yellow. It's a crater basin that's sitting right in the middle. John Ward described something similar sitting in the middle of Kau, except it was filled with basalt. In this case, it's filled, in the case of Angola, it's filled with sterile sand or mudstone. 330 million tons of this stuff has been excavated. Crater sediments. So right now, the open pit at Katoka, after 26 million years of mining, is at about a depth of 240 meters, which is over there. And so the future of this open pit is in primary volcaniclastic kimberlite with no crater-facies material or dilution in the picture. And right now, Katoka is very likely starting studies for underground mining to access this material down here. And that's going to cost a lot of money. And so one has to think about that very carefully. If you look very carefully at this extended abstract from Vladimir Pervov, he says that 35 of 70 pipes near Katoka contain craters with sediment infill. 50% of the kimberlites in the area around Katoka that they have worked on at Katoka have a plug of crater facies waste material that's sitting in the middle of the open pit. And so there's a massive economic impact of about 200 meters of post-emplacement erosion. In other words, this is 240 meters deep. If you eroded this down by 200 meters, it would make a big difference to the mining and operability or profitability of an open pit mine in Angola. And we will look at that problem as we go through the talk. So we jump to the southwest of Katoka to a project called Altuquilo. Here's just one cross-section from a kimberlite called OC16, Altuquilo 16. I'm just showing this cross-section. It's a very big kimberlite because it has a similar structure to Katoka. There's Kalahari sand sitting over the top. There's about 40 or 50 meters of that. Then there's crater-filled sand, that's waste. There's some resedimented volcanic clastic kimberlite. And interestingly enough, also interpreted a fairly horizontal upper surface to what is called primary volcanic clastic kimberlite. And one of the things we've done at Altuquilo is we've relied a lot on magnetic logging. So you can see some profiles downhole of the magnetic signal of the kimberlite as we logged it. Obviously, the Kalahari sand has no magnetic signal. The crater facies sands have very little, but here and there you can see little bits of kimberlite. There's a bit over there. There's a bit over there, a bit over there. And then similarly through the resedimented volcanic clastic kimberlite, you can see how variable the proportion of sand to kimberlite is in that part of the hole. And once you hit the primary volcanic clastic kimberlite, it's all fairly magnetic. So that's a very useful aid in logging. But there are also other useful geophysical signals. You can use gravity, EM, and then I've forgotten the fourth one. But we used magnetic logging a long time, very, very effectively. I've covered the Kalahari cover and the crater infill. It impedes access for testing. In other words, if you want to get to the primary volcanic clastic kimberlite, you have to drill through, in this case, about 200 meters of other material just to reach your target over there. And in a mining scenario, all of this would be pre-strip, and that will cost money, capex. Out of AC16, there were low grades where we were tested. And where the tests were basically on the edge of the kimberlite system over there. You can see there is AC16 in this magnetic image on the right-hand side, and it outcrops in the river valley over there, and that's where we tested it. Where we did test it, there were good quality diamonds. You can see the picture of the diamonds over there. So potentially if the grade and other parameters could be improved, we would still be operating at Altuquilo, but we are not. There are many more large crater infill pipes on this particular concession, and there's more testing needed to prove up which one of those is usefully exploited in the future. I just want to emphasize that point by putting up a little table. Katoka is 64 hectares in size. Here are a couple of others at Altuquilo, including AC16, which are much larger. And you can see them on this magnetic image, which is published by Wayne Pettit, 2009 in Lithos. There's AC71. There's AC70, 150 hectare kimberlite. AC98 is huge. There's AC16, and so on. We'll see more of this type of thing going on in a little later in the talk. When you drill these kimberlites, this is the kind of rocks you see. The horizontal bedded crater facies sandstones. We've seen some stuff like this. In this particular section is in fact 320 to 380 meter depth. Think about that for a moment. Here's RVK with Cassange blocks. That's basically Karoo sandstone or Karoo siltstone. It's this reddish color over here. It's the country rock, and it forms a diluent inside the RVK. And then once you get to depth, you get to these primary volcaniclastic kimberlites, very uniform, good magnetic signal, clean rock. And that's often, you know, what you want to determine the grade and diamond quality of, but it's, in this case, it's very difficult to reach. We're skipping to the northwest of Katoka now to go to Kamafuka, Kamazamba. Just the point I need to make here is very large, very deep, low-grade craters are preserved. There's an inferred resource, very low grade, but a lot of it. Over the 0 to 150 meter depth at the Southern Era 2000 drilling. Nothing has happened to these kimberlites since 2000 because of this sand crater-filled sand-filled crater problem, and how you turn that into an economic resource. There are obviously other kimberlites around Kamafuka, Kamazamba. Not very little is known about those kimberlites. I expect that some of them will be have sand-filled craters, others may not, and we'll see the reason for that in a moment. Down south in central Angola, De Beers in their previous exploration drive did an excellent job on the Dando Kwanza concession in the B province. They discovered 30 new kimberlites, 39 new kimberlites, and reconfirmed 5 legacy pipes during this period. They're smaller pipes, they're less than 1 to 17 hectares at surface, and 14 of the 44 that were tested for microdiamonds had low grades. But the interesting part of their publication is they indicated 2 levels of erosion within the pipes that they did discover. And so diagrammatically, this is what that looks like. You know, soon after eruption of the kimberlite, you erode off this tuff ring, and then you're left with this brown stuff, which, guess what? That's crater facies sands and RVK. Down here is the primary kimberlite. And if you erode, in their case, 250 meters off, then you end up over there. And what you've got exposed at surface is the primary kimberlite, and you've removed all this diluted crater facies sandstones. Erosion has a very important role to play in the view of what you want to go exploring for. If you go for big kimberlites in Angola, you're very likely going to end up with a sand-filled crater problem. If you go for the smaller kimberlites, that sand-filled crater may well be eroded away. So let's see how that plays out in a different project in Angola. It's the Lulo project. And just by way of orientation, 30 kilometers to the east is the boundary of the Altoquilo project. And let's look at this topographic map of Lulo to begin with. This plane, this peneplain at the top here, that's at 1,200 meters above sea level, which is much like Altoquilo. And these are Kalahari sands, and then you go through the Kalonda stratigraphy. This is an eroded basin. You can see the erosion. Down here, we're at 1,000 meters above sea level. So there's 200 meters of landscape erosion. And as luck would have it, the Lulo project has a huge amount of kimberlite targets right in this river valley. Over here, we'll see their magnetic image in a moment. But to add to that inventory of kimberlite, they also have a lot of very nice diamonds in this river called the Caquillo, which they are mining. This is their alluvial mining blocks in red. And what they're getting out of these alluvials are these diamonds over here, including a large amount of type 2s. And they have 28 legacy pipes on this concession and an air mag survey with about 250 targets. Before we get to that air mag survey, let's just look at what they've been doing in terms of alluvial production since 2015. These are again data that are available in their annual and quarterly reports. So we can see how many special diamonds they are recovering out of the carats they're producing. It's becoming quite consistent as a proportion of their total carat production. What is not that consistent is the average price point that they're getting for their alluvial diamonds, because one of these large diamonds can have a very variable $1 million number attached to it. Back to the geology, and in particular, the aeromagnetic survey from Lulo 2008. They did a air mag survey. There are many, many large kimberlites on this concession. Here's the strip that they chose to fly with detailed air mag. This is their alluvial production scenario that I've just highlighted. The block in yellow over here is highlighted at the bottom over here. Look at these numbers: 30 hectares, 9 hectares, 29, 30, 34, 21 hectares. Very large, many, many large kimberlites. However, we know that there's 200 meters of landscape erosion over here. I just have to make these points on the sides to test and prioritize and bring to book these large kimberlites. It's a huge geoscience challenge, but it's also an incredible corporate challenge. There are partners, finance and legal, strategy and timeline that you have to all get right to be able to bring these resources to book. And just to emphasize that point, look at the timeline over here. They knew about these magnetic targets in an AGM in December 2010. This is their kimberlite exploration update 2020. It's already 10 years past before they actually started to get to grips with these primary sources. When they do, and they drill them, what do they find? They find kimberlites that have been eroded. So they don't find a big thickness of crater facies or RVK. It's about 40 to 100 meters when they do drill them. There is some PVK at surface. And we can confirm that the craters here have been eroded by about 150 meters. And so it supports bulk sampling of the non-sandy RVKs and the primary volcaniclastic kimberlites that are a prime target for kimberlite exploration in Angola. This is what that looks like. Here's some 2 bulk sampling pits. They're actually sampling primary volcaniclastic kimberlite in both of these pits. And so they can do that because this is accessible. It's not sitting underneath hundreds of meters of sand. So far, they've tested 4 pipes. I think they're shown in initial processing complete in green on this image over here. These light green ones, those are the ones they've tested. They have recovered type 2 diamonds, but they have very low grades at this time. Wait up. We'll hear more about this project in the future. You can see that in their update over here, this is their Q1 2022 activity report. They have big plans. And we will hear more about this project as time evolves. I just wanted to give some low-grade context. The previous slide had some very low grades on it. I just want to give some low-grade context here, and the low-grade context comes from northern Lesotho, where we know that you can develop very large open pits, because this is a Google Earth image of the Tseng main and satellite pipes, where a grade of less than 2 carats per 100 tons at a very high price point gives you a revenue of $35 a ton. At Matai, the revenue is about $20 a ton. And as of yesterday, I got some numbers for coal, roughly 4.5 carats per 100 tons at $331 a carat. They are sustaining themselves as potentially a marginal operation, but doing so by paying attention to their geology at a revenue of only $15 a ton. So that's the break-even point, or very close to the break-even point for coal and for operating a mine in the northern Lesotho context. And I don't see any reason why that couldn't be the break-even point for a mine in Angola. They're like what Blue Carper and their partners are exploring at Lulo. However, there's some other things that you have to bear in mind. There are many other kimberlites in Lesotho, as we can see on the right-hand side over here, by the red symbols, where there are no diamonds or diggings on top of the kimberlite. In other words, there's a lot of barren material around when you're dealing with this low-grade context. And so you have to pay attention to differentiating things that don't matter from things that do matter, which is a challenging task all of its own. I just have a thing on the side here, on the right-hand side. That's a stamp that was issued by Lesotho in 1971, during the time of the first international kimberlite conference. They recognized that in the Lesotho highlands, they had the remnants of kimberlites that were once much larger, had crater facies on top of them, and that they were eroded. And so we are playing out the same game in Angola, and it's kind of iconic that it comes around after this amount of time. I just want to point out the location of Sekamang. We'll be talking about that tomorrow or the day after. Second last slide in my presentation is about the future of Angola and diamonds in Angola, and the future is very closely tied to this kimberlite called Luele. It's on the Luashi concession, so it's known as the Luashi, either Luele or Luashi. If you look on Google Earth in December 2020, you will see there's another open pit starting up. It was discovered in 2012, 2013. By March 2016, they claimed it to be a 100-hectare pipe, 55 meters of cover, roughly 1 carat per ton grade. December 2019, they had spent $200 million on this project. They stripped 20 million cubic meters of sand to collect a 450,000 carat bulk sample. At that time, they assessed the diamonds at $90 a carat, which means the revenue potential is around $90 a ton. You know, obviously, you can make good money on that. You just have to build the mine first. This is how much they've drilled. As of March 2021, they were aiming for 5.7 million carat production in 2023, and eventually it will be a 400-meter deep open pit. That's another thing to look forward to in Angola. I think we've covered the first point nicely. Diamonds from Angola are very similar to what we see in the rest of the SADC region. There's a very high quality at Kumutwe. More of those can be discovered. There's exceptionally high quality at Lulo. We believe the primary sources are nearby. Finding them and constraining them is going to be an interesting exercise. It's something we have to watch. Kalahari cover and sandfilled craters, they restrict economic outcomes. They are present in Angola. They restrict economic outcomes because you have to dig them out, but it can be done, as has been demonstrated at Katoka. They restrict access for bulk sampling. So from an exploration point of view, this is a problem you need to resolve. And erosion has a massive impact on the way you view kimberlite potential in Angola. The diamond sector in Angola has undergone and is still undergoing a revival. In September 2011, they put in a new mining code and mineral investment contract in place that gave you security of tenure. It's a huge step forward. In July 2018, they had a new rough diamond sale and marketing policy. That's changed the game a lot in Angola. And as of August 2021, there's an $80 million diamond hub that's been opened in Sarimo. There's a picture of it. That's a manufacturing complex and cutting and so on. Thank you all for your time. I think that's the last slide.
Thank you very much, Herman. That was very enlightening. Very well illustrated talk. Very interesting. We can open the floor for questions and comments.
Okay, thanks, Herman. Thanks for an excellent day from everyone, and thanks for a good presentation. I mean, just a comment from me to them. We obviously have a very similar situation in Southern Africa, particularly sort of going west of or going off Cratton towards Prisco with all our alluvial deposits. And if you see what Angola's done, you beg the question, why aren't we doing the same in South Africa? And again, if you see the investment that's going into Namibia, why don't we do the same in South Africa when it comes to particularly our alluvial diamonds? And hopefully next week, Lyndon de Malon and some of the alluvial guys will just will certainly highlight the potential of that area.